SPLASH' 2023. It's the 30th SaaS. It's very exciting. We have a fantastic program with 20 papers, 4 invited talks, some other sessions. We have the PC report and Radia Cuso prize. So lots of things and to have fun. We would like to thank the SPLASH organizers for all the help, Vasco and his teams, thank you, and all the people here helping us out. We'd like to thank our sponsors, Google, the ENS Foundation, Meta, Absinthe, Amazon, Springer, and the IMDEA Software Foundation. Thank the PC members, the authors, the session chairs who will have to do some work. The previous chairs, including Katerina and Gagandeb, which are very extremely, and all the others were extremely helpful with all their material. We will collaborate and provide material also. Proceedings. The proceedings, Springer dropped their ball in several ways. First, because they were supposed to be printed proceedings and they dropped the ball, and then they were supposed to put the proceedings online and they also dropped the ball. I don't know why, because we were totally on time with the things. No? So maybe they appear sometime. But in the meantime, we've just put all the papers on the program. So you can just access the papers from the program. So we have, let's say, zero impact from this lack of seriousness of Springer. And with that, I pass it to Jose. Has a couple more comments.
Thank you. So I have a few comments, just minor comments about the organization. The SPLASH organization added 2 items in the attending menu. You can consult them. So if you are a speaker or if you are a session chair, we recommend you to, well, we ask you please to go and follow those instructions. Those are the usual things that just come 10 minutes before the session. If you are a speaker, to try, or presenter, to try with your laptop if everything works. If you're a session chair, we ask you to come like 15 minutes before. And there's many more minor details, so please go there and consult that information. Additionally, there is some Discord channels. As you know, SPLASH has a big dependency with Discord. You have to go there and see if you are an organizer. There is a lot of information there. So especially for people who is attending online, there is Discord channel for questions and answers, and if you go there, there is a sub-channel for each conference. You click on SaaS, and there you will see more channels for each of the talk. So if you want to see the questions from remote participants, or if you are a remote participant and want to make a question, so please go there. And this is a place where you have to ask. And well, I have also other notes that reminder that on Monday afternoon, after the invited talk on Monday afternoon, there will be the PC report and the Radia Cuso session. I think that's all.
That's all. Yes. With this, we pass the stage to Katerina, who's the chair of the first invited talk, and whom we thank for bringing very young participants to SAS, future abstract interpretation researchers.
Thanks.
Thank you.
So good morning, everyone. Welcome to the first session. So we have a keynote and a talk. And the keynote is given by Evan Chang. He's an associate professor at the University of Colorado Boulder and also an Amazon scholar. And he does excellent work in static analysis and with a particular attention to the challenges that bring modern software applications from Android to Objective-C, JavaScript, TypeScript, and so on. I won't say more. The floor is yours. Thank you.
Thank you, Katerina, for the lovely introduction. All right. So thanks, everyone. It's such a pleasure and honor to be here at SAS. It's, of course, one of my favorite venues, and with all of you great folks. This is some joint work with some students past and present at the University of Colorado. So this talks about some work over several years now at this point. So, all right. So let's get started. Okay, so we're going to consider one of the most important problems of our times, of course, that unfortunately Angry Birds has stopped. of course, this is a crash in an Android application. And in today's modern world, such a crash has significant consequences, right? It's magnified by the crowd. That is, in order to upload your app and get it used, right? You have to put it on the Play Store, and on the Play Store, then you're subject to the reviews and the whims of the world, right? That is, reviews might say if your app crashes, right? Oh my gosh, it's crashed, it freezes. Maybe it's sluggish, and so therefore it must somehow be spyware, right? And that forces, the developer, right, to cry for help. Right, to that, I don't know how to fix this correctly, and my boss is like on me to get this done right away, right? Okay, now, of course, with these big fixes, maybe this is an opportunity for static analysis. And of course, I'm being a little bit silly here, right? That about Angry Birds, but Android is used everywhere from, in satellites or in tractors and so forth. But also, we consider it as a model system for thinking about event-driven systems, interactive systems, whether it be Node.js, React, or ROS. Right? Okay, so to look at these challenges, let's ask the expert Android developers. So we found this nice talk on the internet about how Square handles Android crashes. So here's this net summary of the talk, right? One, it's kind of inevitable. It's not necessarily even your fault, right? Maybe the framework has been modified in some way that causes the crash. So what do? Well, you log as much information as you can, so for when it happens, you know something, right? And then you check conditions to maybe crash it early and fast, so that it's more likely that you see it in testing, right? So my net summary is something like, well, you want to see crashes as early with the best possible history and context information, right? But so suppose we're lucky and get a crash, now what? Okay, so, well, here's essentially such a crash, in a different app, but like in an open source app. And here's an issue, a very nice issue in this Attenapod app. It's actually, if you're looking for good issues, we found lots of great sort of well-documented issues there in that app. But anyway, here what it says is that, okay, there was a stack trace, right? That there was a crash, there was an illegal state exception, cannot execute this task. Because it is already running, but why? Okay, so we examine the stack trace, and we find that the only app code in the stack trace is this callback where the framework is already in the legal state, right? But what is the callback that came before that caused this app to be in a bad state? And if you will, that's my summary of, what you want to do is log as much information as you can so that you know what might have happened, right? So this is some bug from violating some framework protocol rule, so maybe implicit framework protocol rule that we didn't know about until we saw this crash. Okay, all right, but there's actually more good information in this issue, that there's some discussion here. And well, first, it was actually fixed. In my opinion, like, wow, and with this very limited information, it was somehow fixed, right? And then what I pull out here is that, like, well, I haven't really found out how to reproduce this, but this is the only scenario that makes sense. And then goes on to describe that scenario, which is, quite amazing, right? That these expert developers have some expert mental model of what callbacks could have come before, right? To understand, just like, what is the possible way to fix it? I can fix it because I know what could have been the scenario, what must have been the scenario to cause this crash. Right, so the issue is not really, I don't know how to fix this correctly, but actually, I don't know, maybe how we can help as static analysis folks is, I don't know if this fix is really a fix. Can we actually do verification and verify that such a fix is good? Right. So to me, this is the opportunity for static analysis. Okay, well, let's first kind of get into the heads of like becoming an Android developer. So let me tell you a little bit about Android callback-oriented programming, to the best of my ability as a non-Android expert. Right, so you implement an app, some app code, but of course, you're surrounded by the ginormous Android framework, where you implement some callbacks in order to sort of connect with the framework. So when you open your Android 101 textbook, the first thing you hear about is an activity, and what an activity corresponds to is roughly a screen on your application. And so you implement some callbacks to react to events, such as your activity being created, so onCreate, or your activity be destroyed and onDestroy. And then if you continue on in your sort of Android 101 textbook reading, right, then the first thing you hear about is this notion of an Android activity lifecycle. That is, you have a bunch of callbacks that you can register to hear about, like whether your activity has been resumed or paused because maybe your activity has been backgrounded, your app has been backgrounded. Right, so, okay, seems good, right? The control flow in your app is dictated by a lifecycle ordering of callbacks, right? Seems so far so good, right? Okay, all right, so let's dig in a little bit more into this particular issue. Well, maybe you want your app to do something, so you have some button, right? And then in order to respond to the user clicking the buttons, right? Then, I have to register another callback, some listener for buttons, like this onClick. All right, so I have to update my diagram here, right? And then I read a little bit more, and I see that, okay, an onClick can only happen when its activity, whatever that is active, right? And I guess so. It's somehow the click can only happen inside when the app is between resume and, or when the activity is between resume and destroy. Okay, still so far so good. Okay. Now, so inside this app, there's this async task execute to start some sort of background task. Okay, and this is actually where the bug happens, is that if the user can click somehow twice too fast or something, and then they'll start this task again, and the sort of protocol is that you can only start it once. Okay, all right, but when your task is done, you have to do something, right? So afterwards, you need to know when it's done, so then you register some other handler for when the execute is done, so this onPost execute. And all right, so now it gets hard for me. I don't even know how to put it into my automaton diagram anymore, right? So I have some onPost execute. Well, it can't happen anywhere. It can only happen once because your task can only finish once. And actually, it can only happen after the executes has been called. Okay, all right, so right. And then inside that execute, then, well, maybe when you're done with that, whatever the user's done, or that background task, maybe you just want to shut down this activity, so you make this call to finish the activity. And what we discovered in the course of the work is actually, if you ever make such a call, then there's more edges here that's not even in your textbook diagram of the activity lifecycle. Okay, so what's the net summary of this very long monologue on this slide, right? Is that really the lifecycle framework model gets out of hand quite quickly and is not static. Okay. Okay, so maybe some Android expert developers are in the room, maybe, and might say that, oh, well, we could fix this because async task is deprecated and not even used anymore, or really recommended not to be used anymore, maybe because of this complication. Okay, but here's another issue. Same app, same expert developer, 3 years later. And this time, using the much more modern RX Android framework for handling such tasks. And it's definitely a much cleaner framework and much more readable code, but fundamentally the same issue is still under there. Okay. All right, so now back to being static analysis folks here, right? So let me pop up a little bit and talk about static analysis for verified software. Okay. Stuff that we are all familiar with. Well, so okay, so you give me a program, right? And we here in this room, right, implement some verifier based on static analysis, right, to then issue some proof or issue report, right? That is, we want to derive proofs that our programs are safe. Here we want to prove the absence of a legal state exception. Right? And we all know that we do that by system examining the program to simulate running on all inputs, right? That is, using whatever favorite techniques, interpreting abstractions, transforming predicates, checking models, inferring types, right? And then all inputs is then, instead of concrete inputs, we use formulas. Right? Okay, so this is the idealized story. But I want to talk about two ugly truths that we sort of tend to sweep under the rug, right? Whether in papers or when we sort of teach students because we don't want to expose them to the sort of dirtiness, right? Okay, one is well known, and actually both of them are known, right? But one is talked about a lot more than the others. Okay, one that's talked about more, of course, is that most of the time we don't get proofs, but we get some issue reports, right, of maybe bugs. And of course, this is the well-known, often talked about, right, false alarm problem, right? To soundly get proofs undecidedly necessitates imprecision and the possibility of false alarms. We just hope not too many. Okay. All right, but the other one is that we don't really have the program, do we, right? We have some of the code, right? We might have to like patch it up, right, with library models. And therefore, like, when we patch it up to get the program, right, then, well, we don't know really if we have a proof. Well, again, let's suppose we're in that good case, and our tool said proof, right? I don't know if we really have the proof, right? Right, so to get a system to analyze, we have to somehow model the missing code in our, Swiss cheese, right, to plug those holes, right? So, but unsound models can lead to missed bugs, and we just hope not too many. Right. Okay. And of course, if we think about the context of what we were just talking about in Android, right, of the app, right, it's really some tiny bit of small code, right, surrounded by the big Android framework. And we're essentially saying, oh yeah, we're going to sit down and write that full Android model, right? Right. And, and that's really the question that I want to talk about today. Okay. All right, so let me dive in a little bit more, right, and first come back to that kind of textbook picture of we have the program. So this is the basic program analysis assumption, right? That we're given a closed system, then we have main, some textbook closed system, make some transitions, maybe make some more transitions, blah, blah, blah. And eventually, whatever. That is, we're given a transition system, all right? So as a premise, we're given a transition system, and then we compute a fixed point in an abstraction, and we spend all our time thinking about awesome abstractions and stuff, right? Okay, cool. All right. Okay, but again, this in practice issue, right? So we have to somehow manually model the missing transitions, right, for our Swiss cheese, program, right? So, and sometimes those transitions drop out, and there's like, we have to write some library model. Okay, it's painful, but it seems okay. We get pre and post conditions, or use types and so forth like that to get some model for some code that we don't have, that we understand, right? And I guess my first point about event-driven frameworks is really just that. Well, of course, a lot more of those transitions are gone. And we don't even have a main, right? It's just, in fact, that drops out, right? We just have a bunch of these little callbacks on resume, on destroy, on click, right? And we know that there is some sort of thing about, well, when is this callback possible, right? When is this event-driven callback enabled, right? And, we're missing that main driving what's called the callback control flow sometimes. Okay, right. So all right, we just have to sit down and write the Android framework model, right? Well, but it's really complex. Hundreds of API packages, thousands of API classes, tens of thousands of API web methods. And this is like years ago, and it just keeps getting bigger and bigger, right? And worse, right, this can change from version to version and platform to platform, right? Are we gonna keep doing this, at the speed of, of Android framework updates, right? Okay. So, right. So net summary, right? The enabled callbacks change dynamically. There's too many missing transitions to feasibly model soundly and precisely. Okay. All right. So that's really depressing. Okay. Should we just give up? Maybe we just call it a day or something. Okay. So this talk is about giving some hope. Okay. About starting out with some goal-directed abstract interpretation. Right. So that given a transition system, what is the premise here is that, okay, well, instead of maybe fully computing that abstraction, right, like what we want is maybe we're given some error goal that we want to refute. That is, maybe we're not going to prove the full program safe, but just this one illegal state exception that we saw crash, right? Right, that execute task can't run, right? That is, we want to prove that this one error is unreachable. We want to provide help in this. I don't know if this fix is a really fix, at least for this particular assertion. Okay. So then, if we were just taking that picture, then we might kind of like start from there and work backwards and so forth to see whether we can sort of determine that it's not possible. Right? It's like the same picture, just backwards. Right? Compute a fixed point backwards from error in an abstraction. Okay. But the nice bit is that, well, the rest of the program is completely irrelevant if we only care about refuting this one error condition. But we're still doing the same thing. We're over-approximating backwards reachability from an error goal, again, to contradict the initial condition. And of course, this is not like, this is like stuff that's been going on, in many different places, including stuff that I've done in the past year, right? Of course, that's related to the idea of necessary preconditions, just kind of phrased slightly differently. Right? And of course, it goes back to, the notion of forwards and backwards being complementary and being able to define goes back, a long time to Cousseau in at least 99. Okay. All right. Okay, so if I might digress from the main storyline for a moment, just to kind of dispel with some sort of confusions about this very generic term goal-directed analysis, I guess. I'm focusing specifically about this notion of refuting an error goal. But something that might come up and sounds very similar as well. Maybe you want to witness an error goal. You want to witness a crash, right? And then we're in the world of under-approximations. Which again, I'm not considering today, but of course, there's lots of related work in that space. Very, like under-approximate backward symbolic from way back, but also very hot these days in terms of talking about incorrectness logic, right? Combining over and under approximations and testing and symbolic execution and so forth, right? Sounds very similar, but slightly different sort of goals, right? Okay. There's also like the idea of doing still that sort of forward global proof, right? But maybe refining with some sort of error goal. So to compute backwards to refine a forwards from initial abstraction, right? That we want to refine an over approximation for exhaustive proof while witnessing errors potentially, right? So like to kind of change the abstraction somehow, maybe rerunning the analysis after we've learned something more. And of course, this is the idea of like CGAR. I think, in this very global top-level picture also like PDR, and we've also done some work in using kind of goal-directed thinking, right, in doing refinement. Okay. All right. Okay. So back to the top-level storyline, popping back. So what I want to say is that, well, also this goal-directed thinking enables some targeted modeling of these missing transitions. Right? So getting back to our picture, right, it's like in our event-driven framework where all those transitions have fallen away. That we have our callbacks. Can we just, if we only care about refuting an error goal, right, in the event-driven framework, right, can we only model these relevant missing transitions? Okay. That is, can we do some sort of targeted or lazy modeling of the callback control flow just to consider just these relevant callbacks? Okay. Right, and I think, from my perspective, this is essentially what we're trying to do is, in static analysis, mimic what this sort of expert developer, is essentially saying. Right? Okay, so. All right, so for the rest of the talk, right, we're gonna take this picture. Okay, and the first bit we wanted to a little bit look at is that, well, if we really are forcing ourselves, we just have app code, then let's think about this app framework interface, right? Can we, think about, like, what is that core model if we really only have app code? Can we define a transition system where we just have app code and app-only transition, so to speak, right? Some sort of core calculus model. Okay, and that led us to this idea of enabled and allowed messages, which I'll just say a few words on. Okay, right. Then I'm actually going to call back to some, much older work of ours, right, in trying to tackle this problem, right, and of the idea of like being able to pick out relevant callbacks. And that led us to this idea of, well, we can do selectively control flow abstraction, if we're given a goal, right, and that allows us to identify some relevant callbacks, and we sort of define this notion of a relevance relation, conceptually, right, okay, all right. We're then kind of putting those two older ideas together is what kind of led us to where we're at today, right, of being able to only model these relevant missing transitions, right, and this idea of abstracting message histories, right, which allows us to decouple the temporal logic specification that we might want to make about callback control flow from actually just an app-only code analysis that really, really just looks at the app. Okay. All right. Okay. So let's dive in. Okay. All right. All right. So back to our sort of huge, like, Android is crazy picture, right, or something, right? Let's, for the moment, right, just dive in a little bit more about the craziness, right? Even though we've already sort of convinced it's crazy or hard, right? To just, like, let's just try, right? Can we, do good enough upfront modeling somehow, right? Let's just try to write that pink, picture, right? And, so taking just, this automaton picture, right? It's tempting to say like, oh, let's write, some sort of fake main, some driver that like, just models that sort of automaton, right? That maybe where the, on create state is where we start, right? And so then, we'd make some sort of, call to the app that we're trying to like model the driver for, right? It's like the on create callback. So that little dot, dot, dot's supposed to try to represent that interface, right? And then if we were able to do that, and again, this is why this is super tempting, right? Is that, oh, well, once I sort of combine my app code with this driver model, then I'm back into the sort of nice, clean, whole program world, and I can just pass it to my verifier, and I don't have to think about this sort of yuckiness anymore, right? This sort of ugly truth. Okay, all right, look, but some things, right? Well, okay, I need some activity to call, right? So I need some activity that's from the app, okay? All right, and then I'm in the resume state, right? And then, well, I need some activity from the app. But this is supposed to be the same one, right? This picture is supposed to reference, oh, it's about the same one, right? But now do I have to interleave it with other activities? All right, okay, but let's just say we do the same, right? Okay, then maybe I, have a choice to go into the on pause or on click state, right? So, but again, like if it's like in the so let's say we're in the on click state, right? Then we have, okay, some button, here that needs to go there, or, but oh, do I need it to be all buttons, I guess? Or but it's really all buttons that's attached to this activity, right? So now I need to like take the app again and do some sort of analysis to generate a model to be able to do more static analysis. So, that sounds scary. And then, of course, I have this listener here, this other listener object, for some button from the app, and of course, this state is only possible, after this listener has been registered, so how do I capture that, right? Again, this is kind of the same picture we discussed already, right? That the challenges are there are arbitrary many app instances, right? That the callbacks are enabled dynamically. So I think it's really, really hard to be sound enough, to be precise enough, and to have covered enough. And I've just like touched a couple different sort of framework classes, right? There's nothing about Arc Android here at all. Right? Okay. And of course, we observe this, but we're not the only ones to observe that it's really hard to be sound enough. Right? Okay. So what's the pragmatic approach here is basically just to ignore and say, oh, there isn't no life cycle description or something like that. This is essentially done, as far as we can tell, by all the industrial Android analysis tools. Just assume every callback is an independent program, right? And then just prove what you can prove there or whatever, right? But anyway, seems like a real need to re-examine callback control flow constraints. Okay, all right. So if we just back up, and just kind of like don't even think about the static analysis for a moment, right? And just observe the sort of concrete framework app interface, right? We make this little picture. Is that, okay, I'm gonna draw like a sequence diagram of sorts, right? Like a framework timeline and an application timeline, right? And then let's say, at the beginning, the user clicks some button, the framework receives that, and then issues some sort of on-click callback to the application, so listener to on-click. Right, so a callback is where the framework invokes an application method. And then in response, or inside that callback, for example, like the application might invoke some API calls back to the framework. And just by analogy, or we're going to define a term here, right? That a call-in is where the application invokes a framework method, so in complementary. Right? Okay, so maybe that callback is done, right? So the on-click returns to the framework, and then another event happens, right? The background task finishes and invokes the async task on post-execute, right? So now on post-execute can't happen unless that execute has happened before, but in this timeline, this is a valid sort of timeline. Okay, so anyway, this picture says, well, yeah, the event-driven framework uses callbacks to notify the application of events, and the application uses call-ins to affect how the framework invokes future callbacks. Okay. Okay? And just so that I don't keep saying callback, call in, blah, 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 right? Because it's really just generically this sequence, right? I'm going to define a term messages to be either callback or call in invocations with these actual arguments, with these, actual concrete, instances. Okay? All right? Okay, and again, it's not the code that I'm talking about, but like these invocations here, and just using the sort of OO terminology here. Okay. All right, so suppose that the timeline went a little bit differently, right? That the background task is a little bit longer, right? And the user, clicks in the middle, right? That's exactly where, this bug originally happened, right? Is that if you just have the click listener and you have execute, then, you have two executes, and then this is where the exception happens, right? You can't call execute on the same async task. Right? So seeing this picture, right, it suggests a very natural sort of bug fix. And roughly the bug fix is pretty close to this, right? Is, just obviously simplified for presentation, right? Is that, well, then that click handler is disabled, as soon as it happens the first time, right? So that you can't actually realize this particular trace, okay? Right. So that leads us to this idea of talking about realizable message histories. That is, if we think about like some sort of ghost state or hidden state, right, that the framework has some set of callbacks that are enabled for it to call, right, like the listener on click at the beginning. Right? And the application simultaneously has some set of call-ins that it's allowed to make. Right? So like async execute is initially allowed, right? And then afterwards, after the async execute, then there's a new enabled callback, the onPost execute. Right? And then afterwards also, it's no longer allowed to call execute, otherwise an exception would happen. Right? But it can also call button disable, right? And then maybe it calls disable, right? And that's the bug fix, right? And then that sort of disables. It disables the sort of on-click callback, right? Okay, so flipping that sort of crossing out, right? Okay, right. So then, so this model state that's behind the scenes here that we've sort of thought about here, right, is that the enabled callbacks model what the framework may invoke next, and the allowed call-ins model what the application can invoke without error. Right. So if we look at this message history, this sequence of messages, right, this defines the observable interface between the framework and the app. All right, so then, we took this idea and did a bunch of others. I mean, in fact, at the time we were looking at dynamic analysis, we were detecting life state races. We called this idea of, callbacks and call-ins by analogy to type state life states, right? And we were looking for such races, right? So you can see the paper for those details. But what I want to focus on here today is, or mention here is, right, is that really this provides a concrete basis for thinking about goal-directed abstraction, of callback control flow. Okay, all right, check my time. Okay, cool. All right, so moving on. Okay, so again, back to our sort of Android is craziness picture. Okay, so again, let's sort of, by magic, poof, all that sort of other complexity is gone, right? And just, again, go back to the assumption that this is a sufficient model to work with. And also, let me simplify for discussion here, to start, right? That let's just focus on proving, dereference is safe. Right? That is like, some sort of nulling out, which actually is quite common, right? That at the destroy, you might need to null out things to make sure you free resources and not have memory leaks, right? And then that we're focusing here on that, is a particular given dereference safe. But even in this much, much simplified model, right? You still have life cycles and many different kinds of components, and all the callbacks can interleave, right? So the challenge here is that verifying safety of dereferences depends on callback interleaving. Right. And we have multiple components. Well, they interact through some shared heap, right? They operate over a shared global heap. And so the challenge in verifying the safety of dereferences is that it depends on the ordering of heap rates. Right. But going back to our picture, if we care about just one dereference, that the safety of a particular dereference shouldn't require reasoning about all callback interleavings, right? A small goal-directed analysis could consider just the relevant ones, right? So how do we be, smarter? Right? Okay. So the core idea of this work that I'm pulling out for the sake of today, right, is that the idea of being able to jump back to relevant callbacks. That is, if I look at my components and I have one, I care about, one callback where, there's some safety property that I want to prove here in that one callback, right? We can find the data relevant callbacks over approximately that sort of modify the sort of field that we care about in question, let's say. Right? And then, so that sort of filters out and drops a whole bunch of stuff as being irrelevant. And then, of course, there's still some things like the destroyer that we don't want to visit, as being relevant. So maybe we can somehow filter those out using some notion of control feasibility, right? That it's after the click, it can't be backwards reach from this click. Right? So what we end up here is with a backwards analysis that sort of jumps between different callbacks. Right? And again, still, like, we've thrown out a whole bunch of the program. The rest of the program is irrelevant. We never even really thought about it with respect to the sort of callback control feasibility bit. Okay. All right. So this data relevance, right, bit, right? Let's look at it a little bit more, right? So of course, this is like if we start out with just the transition relation of a system, right? Given a current location, we output the next locations that we sort of need to visit in our analysis. But if we replace that with a relevance relation that has input also as the current query we're looking for. So that is, maybe we can do this in two steps. One, which is, well, first, we look at the sort of data relevant locations to the current query. We identify locations that can write to the query queue. Right? We can compute this using some sort of pre-passed points analysis or types or field-based or whatever, right? However approximate. And of course, this is a very classic idea, if that's not particularly new, right? That we can follow data dependencies instead of the control dependencies, right? Which yields a sparse analysis. Right? But here, this is completely flow insensitive if I just sort of took this as my sort of next locations to visit perspective. Right? But if we add a filter on top of this, right, we selectively get back some sort of flow sensitivity that we want. And we can choose this at every transition step. We can decide, if we want a different sort of thing, right? That we can filter the set of data relevant locations using control flow and the current program point. Right? That is, if we have this control flow graph, right, we can filter out the ones that are not backward reachable from the current location. Right? And we can also filter any locations that are post-dominated by other relevant locations, the other ones that we choose, where we must visit first from some other location. Right? Okay? But of course, I kind of hid something here, right? Which is in order to have such a picture to do that filtering, I'm sort of essentially assuming some sort of static control flow, right? And in the case of Android, some static callback control flow. But this does become a basis for this sort of targeted modeling idea. Okay. Right. All right. Okay. So now we can dive in there. Okay, about abstracting message histories. All right, let's go back to our original picture, right? Let's try to, verify this fix. Okay, so I'm switching a bit to the sort of more modern version because that code is a bit simpler and easier to read, so compared to the async task code, right? But we're going to actually look at, trying to follow the reasoning to get to this fix. Okay. All right, and only model those relevant missing transitions. Okay. All right, so if we zoom in on the stack trace, just really show you that this is the only app code in the whole stack trace, the only thing that has antenna pod in there, right? Is the callback to call. I know, slightly confusing for our presentation, but the callback is called call. Okay. All right, so that's the first bit, is that, okay, we have to think about there's error somewhere in call. Right? All right, so let's click on the fix. and see a bit of the fix. Oh, this is the change, okay? There's a change that something about unsubscribe, a call-in is made in the change this edition. Right. So the fix here is that call-in unsubscribe somehow, is the fix. And then if we sort of like read a little bit more about call-in and unsubscribe, we learn a little bit, like in the summary here, is that, oh, the callback call, f.call for some f, or for all f, only happens only if, there has been some call-in of subscribe on that f, has been invoked somewhere in the past, and the s.unsubscribe has not been invoked since, right? For all f's and for some s, and I'm trying to get a little bit more precise now. Okay, all right. So what we're going to try to do here in like 5 minutes, hopefully, is like, can we verify this fix with just this one key targeted callback control flow model? Okay, so let's do this backwards, goal-directed reasoning, right? Okay, so we're going to interpret backwards from the error goal in the callback, right? So here's a snippet of that call code with some, simplifications, I suppose. But basically, there's some use of this activity field, and I'm going to represent it as this assertion that the activity better not be null. Right? Okay. So at program location 4, I'm showing sort of the starting goal, which is that there's some sort of abstract message history I'm going to call OKHist here. And then what we want to do is suppose, for the sake of deriving a contradiction, that the app can reach here, this location 4, using any realizable message history. That's what I'm representing with OKHist, and with the error condition that this activity is null, which I'm making a little bit more explicit here with this kind of separation logic bit. Okay. And what I want to say is that this OKHist, well, the concretization of it is that it concretizes to all realizable message histories. So it's a sort of top-like thing, but not quite, in the sense that this realizable says, well, it depends on whatever the underlying targeted modeling that I'm going to do now or later. Right? Okay. Now if I just go backwards to, then pass to the beginning of call, back into the framework essentially, right? Because now the program location that really is, before call is inside the event loop of the framework. And what I'm saying here with this assertion is that suppose that the framework can reach here, the framework location, using a message history where appending the next callback, the f.call, is realizable, and with, f.activity being null. Okay. And this is like what we're writing here with this ordered linear implication, kind of on the right, to represent. And I'll sort of dive into like what that, is a bit, right? Because it's like, oh, what is this appending this thing? Okay, all right. Okay, so what is the meaning of this sort of appending, thing? Is that, okay, so it sort of concretizes to a bunch of concrete message histories. Okay. Now I'm sort of a little bit, for the sake of slides, a little bit, being loose here, right? Well, really, I mean like some concretization of a possible message, right? So if there's a concretization of this abstract message, then appending that sort of concrete version of that abstract message is in the set of possible realizable message histories. Okay. All right, let me give some examples. So suppose that OKHist, or a set of realizable message histories based on whatever background model we're working with, looks something like this, right? So one of them that we've already thought about, right, is that there's some subscribe and some number of calls, and then eventually call happens. Right? Okay. Of course, I could also have a different number of things before call or after call. Right? That's these different dots. Right? Or some prefix of that, right? Like I got to the subscribe and I haven't yet gotten to call. Right? Which of course could also include kind of the empty sequence, right? That empty message history. Empty history is for the initial history, for the framework, main, right? Like, oh, the framework hasn't started yet, hasn't done anything yet. Right. Okay. Right. So then what we're doing here is essentially filtering out some things, right? Is that well, the next thing to be done is call. And so that's sort of like, that's one that's allowed that we keep, right? That is also one that we allow and keep, right? But the other ones don't end in call, so those are ones that we're sort of throwing out, at this point. Right? And in fact, the initial history is excluded, right? So what this is saying is that, oh, we can't just, start here in the middle where call is the next thing. Okay, so, in short, in summary, right, the abstract message histories constrain the past with what's necessary to reach the goal in the future. Okay, with these constraints. Okay. All right, so that's as technical as we're going to go today here, right? So to pop back up a little bit, right? So then, to kind of finish the verification, right? The callbacks that are relevant to this particular assertion, right? Well, there's this destroy that does that unsubscribed, so that we saw there in the bug fix. Right? This is relevant, because the f dot activity is nulled there, and actually because unsubscribe is related to call because of that model. So, but if we, walk through high level what the verification would continue is, right? If callback f dot on destroy comes before the callback f call, then unsubscribe must also come before, contradicting the model. The other one that's relevant is the create callback, right? So, but there, if callback f dot on create comes before callback f call, right, without destroy in between, then now the f dot activity is non-null, contradicting the constraint that f activity has to be null. So at fixed point, if the backwards from error invariant of the framework location framework excludes the initial message history, that sort of empty sequence, then the error condition is unreachable. And it's a little bit interesting to observe, right? It's not that we have a contradictory state here at this point, right? The concretization is not empty, it's not bottom, but it excludes the initial message history, and that's where we're deriving this sort of contradiction. Right? And this sort of excludes initial is that, well, you can't start the framework in the middle, right? That's just, the framework can't just be in the middle of the sort of like sequences of that are realizable. Okay. All right. So, so this notion of checking excludes initials and intersecting abstract message histories, and then being able to specify those models, right, using a restriction of first order pastime LTL using SMT. That's what's talked about in our upcoming SPLASH'23 paper. That's going to be given by my student Sean Meyer. So if you're still around this week, I encourage you to look at more of the gory details. All I've done here is kind of set up the problem, right? And he's sitting there in the back as well. All right. Okay. So of course we want to know, does this actually work, right? Does targeted modeling enable distinguishing the fixed versions from the buggy versions using our tool Historia in real callback enabling issues? So what we did is we pulled out 5 fixed issues changing some enabled callbacks. So we didn't even consider anything that are like simple, easy things to prove, right? Things that actually require changing the set of enabled callbacks, right? We got them from 2, pretty like well-developed apps, right? AntennaPod and ConnectBot, they have lots of stars, whatever. And then we tried to compare it with, the sort of no modeling pragmatic approach and the upfront, lifecycle models. So here's the net, summary, right? So here are those 5 issues in the buggy and fixed versions. Right? Here is the number of relevant callbacks and call-ins used. So if you think about all possible interleavings of this, and then if you have things like this or multiple instances, right, that sort of thing, that's a big number. And then we compared it with using the sort of no order pragmatic approach, using infer, and we had to do a little bit of things of like some of those illegal state exception things, so we had to sort of rewrite it to be for the purpose of doing null dereference checking that infer can do. And so we get alarms on all of them. Right? And then we compared it to using the sort of upfront modeling of trying to write down the model. Note, we're not using the flow-droid analysis tool, but just the model that it generates, which is sort of the most well-known sort of Android analysis tool out there, doing some sort of lifecycle modeling, right? So, but then we sort of looked at the model that flow-droid would generate, and then thought about, like, could any possible analysis, no matter the precision, be able to, prove or, and such, right? And this is, the result. And then we did our sort of target modeling approach of writing those little specifications of relating, for example, subscribe and call, right? And of course, this is the bottom line result, right? That all of the instances were able to be correctly distinguished, and that's the challenge, right? Between distinguishing the buggy and the fixed versions, right? Whereas the other tools either alarm or prove or something like that, but never distinguishing the buggy and fixed versions. All right, and these are the number of, those little, that pastime LTL type formulas we need to write, the number of specifications, that kind of targeted modeling, and here's the verification time and the depth. And so we're able to prove these without going too deep in terms of the number of callbacks that we need to go down. All right, of course, now we just picked out 5, well-crafted things. Of course, we're going to get, that good, right? So is this sort of generalizable? Does targeted modeling generalize to prove assertions on real-size, complex, widely used Android applications? So what we did is go to the sort of open source repository of Android apps called F-Droid. We picked apps that were, we just basically based on apps that were well-maintained sort of things. The proxy being that they've been updated in the last 2 years, and the projects were started a long time ago, updated more than 8 years ago. We end up with these 47 apps and 2 million lines of code. Right? Then from that, we took those 5 bug patterns from those 5 issues and wrote some detectors to find those, and we ended up with 190 possible error locations. And let me just put the bottom line summary here, right? And I'll give you the table here. That without modeling, without any modeling, we were able to prove 43% of them. So if you will, those are the easy cases, right? 28% alarmed, right? And then 29% sort of timed out within an hour. We sampled 8 of those alarms and tried to verify with targeted modeling. Right? And from that, we were able to verify 3 of them with just 4 little specs. We found 1 true bug with just 1 specification, and 3 did timeout in the sort of 1 hour we gave it, and we also gave ourselves a timeout of being able to write down the specification, figure out what we need to write down in an hour. So 1 timed out of we got tired of figuring out what's going on, some sort of thing. Okay. All right. So popping back up to the key ideas, right, that we first thought about how do we talk about just the application only? And then if we only have the application, how do we jump between relevant callbacks? And then how do we actually do some sort of targeted modeling to be able to prove cases where the callback orderings do matter? Okay. All right, so to pop up into kind of the take-home message. Right? So one is maybe be goal-directed. That reasoning backwards from goals enables thinking about, enables relevance and sort of distinguishing relevance and irrelevance. And a sort of call to arms here in the second bit is come together. There's no such thing. There is no program analysis, only app analysis. And we somehow have to abstract the interface, with its framework and design abstract domains around that. And okay, let's see. If I may, just kind of also call to arms and plug sort of the next thing we're thinking, right, is that, if we think about that sort of main picture of okay, my clicker died, oops. That, can we, instead of manually modeling those missing transitions, can we do synthesis and synthesize those? That is maybe, can we complete a given transition system consistent with maybe some additional goals? Okay. All right. So with that, I'll take some questions and show off the beauty of Boulder to invite folks to visit, students, postdocs, collaborators, and so forth.
Questions? Okay, I can start with one. Could you maybe give us an idea of the kind of abstractions that are involved in this kind of work, like abstract domains? Or I saw some separation logic here and there, but maybe a bit more
Yeah. So I mean, so the assertions, like I showed, there's, we essentially model the heap using separation logic and such to talk about what fields that could be possibly written and track those precisely. And then the sort of abstracting of the message history is kind of the domain that we've been essentially working on to talk about how do we represent the interface.
Thanks. Other questions?
Thank you. Great talk. If you were made a dictator of Android and you could design the API with kind of a view towards program analysis, could the problem be made easier, or is it just inherently difficult?
No, I think that's an excellent question. Of course, some things could be made easier, I suppose, right? But I think there is an inherent difficulty into the fact that you don't have all the code, right? That and there's really not, every framework has, every framework for an interactive application ends up looking like this, right? You write some small bit of code that hooks up to it in some way, and that's, I think, the fundamental program analysis challenge is that we just can't go with this sort of given the whole program sort of perspective. So
We have time for some other questions. I don't see anything. No? Well, I
there's
have
one more back there.
Sorry, I didn't see.
Yeah, so I'm kind of curious, because you have one slide you show that you are sampled 8 alarms, then you try to verify with target modeling there. I'm curious, you mentioned you with 4 specifications, and you found the true bugs in 1 specification. So how do you get those specifications?
Right. So, this notion that the specifications are ones that we wrote, or Sean wrote here, by essentially consulting the Android documentation or understanding just like a developer would. So essentially, we are very much essentially trying to capture the developer workflow here, right, in the static analysis, right? That like, oh, there's a crash here. Like, how do we check that it's safe? Now, a normal developer probably reads the documentation and sort of convince themselves, mentally through that simulation. We're taking that one step further and taking that sort of mental simulation out into the static analysis and doing that sort of understanding of the documentation and codifying it into a temporal logic formula, essentially.
Okay, so yeah, another question is, I mean, programmers usually they read the code, they never read the specifications. So I wonder if there are some ultimate ways to derive those specifications.
Yeah, no, of course that's so the question is, could we automatically derive the specifications? And of course that's, I think, a promising thing we of course want to explore in some way, right? And that's kind of what I sort of alluded to in the next steps is, could we synthesize those specifications subject to some other higher level specification, like, what are possible, what are goals, right? What are the other goals in the program that need to be either satisfied, either be reached or unreached or something like this, or unreachable, or proven unreachable. And I think that's potential, right? Now, one thing, of course, that any of these specifications that get written are reusable for the particular version. Right? And I would also say that it's essentially there's always this but we have to specify something. Well, you always have to specify something, I guess I'm calling out. Whether it's you specify the whole Android framework up front and complete the program, or whether you can specify bits and pieces that are relevant to the particular assertions you're trying to prove. And we feel like we can get more confidence by doing this sort of targeted approach.
Thank you.
Yeah.
Anything else? Maybe, so you talked about Android, but this kind of ideas also apply to other languages and other kind of applications, right?
Yeah.
So can you say more about this? If it,
Yeah. Yeah, and again, I think we got sort of heavy into Android here in terms of Magnus's questions, could we just make it better, right? Can we just change the framework? And I think it's fundamentally something that if you want to write interactive applications, you're going to have some framework, and I think they apply equally. Now, we haven't looked as closely into others, but we really think of Android as just a model that we can get access to, in the sense that there's open source applications, and it's a complex open source framework that we can learn from. Right. So
thanks.
Yeah. But yeah, I think it applies equally to JavaScript or React or whatever, all these different challenges.
Okay, well, I think we can thank the speaker, and the next speaker can set up.
Thank you very much.
All right, so the next is a regular talk. It's given by Jocelyn Vier, and is a product of shape and sequence abstractions.
Thank you, Katerina. Good morning, everyone. This job is in collaboration with Félix Ridou and Xavier Rival, and it aims at combining an existing shape analysis with sequence abstractions to improve its expressiveness. To motivate our work, let's consider this example inserting a value in a binary search tree. There are many properties we would like to prove about this program. First, we could check that all dereferences of the C pointers are valid. This is the absence of runtime error in this program. Then we could also prove the preservation of structural invariants. Informally, if T is a well-formed binary tree, then the return value is also a well-formed binary tree. But we could also try to prove a much stronger property, that is partial functional correctness. In addition to the two earlier properties, it means that we have to prove that the value is indeed inserted in the tree at the right position. Here, this table shows how existing analysis performs regarding to these properties mentioned earlier. For example, pointer analysis only works to establish absence correctness of pointer dereferences. Second, we have shape analysis based on three-value logic and separation logic. This analysis works well to prove pointer dereference validity as well as preservation of structural invariants. And finally, K-limited graphs works well to prove partial functional correctness, but only on a limited family of inductive data structures. So none of these approaches could prove the partial functional correctness of inserting a novel element in a binary search tree. Therefore, we could ask ourselves how to improve the expressiveness of automatic static analysis over dynamic data structures to prove partial functional correctness. Our work is based upon the separation logic-based shape analysis. It uses a subset of separation logic to abstract memory states. Separation logics take its name from the separating conjunction. These operators groups predicates, and it expresses that the memories described by these predicates are disjoint. And second, to summarize the inductive data structures, separation logic uses inductive predicate. Here I show the example of the tree predicate expressing that C is the address of a well-formed binary tree. We have two cases. The first case is, on the left, is the empty case, where C is a null pointer, and in this case, the memory described is empty. And on the right case, we have the non-empty case, where C is a non-null address of a cell containing a data delta and pointers to two subtrees. As I mentioned earlier, separation logic-based shape analysis can prove validity of pointer dereferences as well as preservation of inductive invariants. But since the inductive predicates forget the content of the inductive data structures, it cannot prove that the value is indeed inserted in the tree. In previous works, the inductive predicates were added set parameters expressing the content stored in the tree. So using capital letters E, in the empty case, the content is empty. In the non-empty case, the content is obtained by considering the content of the two subtrees with the value delta. But this extension is not enough because it cannot reason on the order of appearance of elements, and this is crucial to reason about sortedness. This brings us to our solution, that is to express constraints on the sequence of values stored in the tree. To do so, we had a sequence parameter, capital S, representing the sequence of elements in the tree in infix order. Moreover, if the sequence S is known to be sorted, then the tree predicate expresses a well-formed binary search tree. And we can now express the partial functional correctness of the insert function with this O triple. And we see that to prove this O triple, we first need an abstract domain to reason on sorted sequences, and we also need to combine this domain with the shape analysis to express the content of the tree. In this work, we make the following contribution. First, we designed an abstract domain reasoning over sequence constraints, and we also reason on their content, their length, their bounds, and their sortedness. Then we combine with a reduced product the sequence domain with an existing shape analysis. And finally, we implemented this analysis in the memcad tool, and we discussed its expressiveness, its cost, and its versatility. So now let's describe this abstract domain reasoning over sequences. I will just simply call it the sequence domain for the rest of this talk. The goal of this domain is to abstract sets of functions evaluating numerical variables, here alpha and delta, to numerical values, and sequence variable, here S and S1, to sequence of values. An abstract value of this domain is a tuple whose first element is a conjunction of sequence definition. Here we call a sequence definition an equality constraint, where the left part of the equality is a single sequence variable. Second, we have an element of a multiset domain. We use this element to reason on the content of the sequences regardless of their order of appearance. And finally, we have an element of a numerical domain. We use it to express constraint on the length of the sequences as well as the bounds of the sequences, and this is crucial to reason about sortedness. Now let's describe the main operator of the sequence domain. The guard operator refines an abstract value by adding a novel constraint. Here, let's take the example of assuming the constraint SR equals alpha, that is to say SR is a sequence with only one element, the numerical variable alpha, in the abstract value described in the left. First, the operator simply adds the definition in the conjunction, and then the operator propagates this constraint by adding content, length, and bounds constraints. So, for example, it says that the length of SR is 1, and the minimum and maximum values of SR is equal to alpha. Then the operator folds other definition using the novel one. For example, here, in the definition of S, alpha is replaced by SR. And then the operator performs some constraint saturation. So here it infers that SR is sorted. I show here the rule to infer sortedness of a sequence. Notice that it must perform a quadratic amount of numerical check. And finally, the operator detects and removes cyclic constraints. And if at any step of this operator we detect inconsistent constraint, we simply return bottom. And the guard operator is sound because the return value over-approximates the evaluation satisfying the constraint. With the guard operator, we implemented other operators. The first one conservatively checks that constraint is verified in an abstract value. And we also define the standard lattice operators, that is to say inclusion check, upper bounds, and widening. Now, let's describe the shape analysis with the sequence predicates. First, let's highlight the main challenges of this combination. Recall that the tree predicates only described full binary trees. And here I show the state of the memory at some point during the exploration of the binary search tree, where C tries to find the point of insertion of the new value. So C points to a full binary tree, so we use the tree predicates. But to summarize the partial tree between pointers L and C, the analysis uses a segment predicate tree seg. Since this predicate is automatically derived from the tree predicate, we need to extend the analysis to reason over the content of this segment predicate. The second challenge involves the operators used by the analysis. We have two families of operators. The first one, unfold operators, refined memory state, and the second one, fold, generalize a memory state. For both families of operators, we need to derive the corresponding sequence constraint to be either verified or guarded. So on the expression of segment predicate content, I here show the memory states that I showed earlier, and you see that I also show the sequence stored in the tree. If the analysis says that the segment predicates contain sequence 0, 1, 2, 3, 10, 11, 12, this is not enough. The analysis must also remember where the missing sequence in blue is inserted in the sequence contained in the segment predicate. To do so, the segment predicates use two sequence variables, S1 and S2, each one for each side of the missing sequence. So S1 abstract 0, 1, 2, 3, S2 abstract 10, 11, 12. To describe how the unfolding operator works, let's consider the case of analyzing this small program if L assigned to V the expression L arrow data with the initial state L is the address of a tree containing a sequence S. First, the analysis guards the if constraint, L is a non-null pointer. Then, to perform the assignment, the analysis must evaluate expression V arrow data. To do this, it unfolds the tree predicate. It is then replaced by its conjunction of this possible definition, where the variable delta, SL, and SR are fresh variables. Moreover, the constraints of the definition are guarded in the sequence part of the abstract value. The analysis then notices that the constraints in the empty case on L are inconsistent. So the analysis discards this case. And in the non-empty case, the expression C arrow data corresponds to the value delta. So it is assigned to the value of V. Unfolding a sequence predicate, unfolding inductive predicate is sound because the disjunction of the two resulting states over-approximates the original one. The folding operators perform the opposite operation. It merges several parts of the abstract state into one inductive predicate. Here we have two cases. The first one corresponds to the case where the analysis detects a possible definition of an inductive predicate. Then it verifies whether the corresponding sequence constraint is verified, and then it can unfold it into a full tree predicate. The second case of folding is more interesting. In this case, the analysis concatenates a segment predicate with a full inductive predicate. In this case, the constraint to be verified is simply obtained by inserting the content of the full inductive predicate S0 between the two sequences of the segment S1 and S2. And folding an inductive predicate is also a sound rewriting operation. With the folding operator, we define the other standard lattice operators, that is to say inclusion checking, upper bound, and widening. And with these operators, we designed a sound and automatic static analysis by forward abstract interpretation. Moreover, by checking the inclusion of the final state into the post condition, the analysis is able to prove partial functional correctness. Now let's go back to the example from the introduction, that is to say, inserting an element in a binary search tree. Here, I show the invariant found by the analysis after 2 iterations of the loop. So it states that C points to a subtree of the tree pointed by L, and the sequence of the original tree, that is S, is obtained by inserting the content of the subtree pointed by C, S0, between the 2 sequences of the segment, S1 and S2. And all of the corresponding sequence variables are inferred to be sorted. Moreover, the numerical part of the analysis automatically infers that both N and C pointers are non-null, and that the value V to be inserted is between the maximum value of the left part of the segment and the minimum value of the right part of the segment. That is to say that the point of insertion of V is to be found in the subtree pointed by C. And with this invariant, the analysis carries on a final state to prove inclusion in the post condition shown in the bottom of the slide. Now let's describe the experimental part of our work. We implemented this analysis in the Memcat tool. It is available online. It is also available on Zenodo if you like. And for each test, we only specify 2 elements, the specification of the function we would like to prove, and the full inductive predicates that the analysis needs to use. And then we ask ourselves, what is the expressiveness of the analysis regarding memory safety and preservation of invariant, as well as partial functional correctness? What is the cost of the analysis compared to the analysis without sequence parameters, and what is its versatility? To answer the first 2 questions, we analyze programs implementing classical list and binary search tree programs, including insertion sort, bubble sort, and heap sort. For all of these programs, the analysis managed to prove partial functional correctness. Moreover, we observed that adding sequence parameters improves the precision of the analysis to establish preservation of invariant in the case of deleting the maximum element of a binary search tree. Regarding the cost of the analysis, we show in the 3rd column the overhead of the analysis. We observe that it is between, the analysis takes between 5 times and 10 times the time of the baseline analysis, that is to say without sequence parameters. And for complex programs such as insertion sort, the overhead is much stronger, up to 30 times. We found 2 elements justifying this cost. The first one is that most of the time of the analysis is spent in numerical domains. So in the 4th column, we show the percentage of the analysis spent in the numerical abstract domain. And we can think of 2 elements justifying this. First, the quadratic cost of sortedness checking I mentioned earlier. And second, we also observe that length constraints are very expensive because the highest value, the highest percentage of the time spent in numerical domain is obtained for insertion at a position. And the second element that could explain the cost is that the sequence domain requires 1 more iteration of a loop for the widening to converge. And in the case of insertion sort and bubble sort, we have nested loops. So it's 5 more iterations. To test the versatility of our analysis, we analyzed programs from real-world list libraries, that is to say the Linux list library, the FreeRTOS list library. FreeRTOS is a small operating system for microcontrollers, as well as a generic data structure library. All of these libraries are instances of circular doubly linked lists with a distinguished header, and they also implement various features. For all of the functions, except two, the analysis established partial functional correctness. It fails to establish this property for mean and max extraction in the generic data structure library. But we also observe that adding sequence parameters improves the precision to establish memory safety properties. Now, let's conclude our presentation. So, on the question of how to improve the expressiveness of static analysis, of automatic static analysis over dynamic data structures to establish partial functional correctness, we first design a novel sequence abstract domain, and it is capable to reason over their sequence as their order of appearance, but also of their content regardless of the order of appearance, their length, their bounds, and therefore their sortedness. Second, using an abstract reduced product, we combine this sequence domain with an existing shape analysis based on separation logic. This requires to derive at any step of the analysis the corresponding sequence constraint to be either verified or guarded. And then we implemented this analysis in the memcat tool, and we observed that it was expressive enough to prove complex programs such as sorting algorithm, and versatile enough to be applied on real-world list libraries. Thank you for your attention. If you have questions.
Questions?
Yeah, thank you for your talk. Are you aware of this work on verification of or shape analysis with size, back, and other numerical constraints? This is a paper like 10 years ago that looked a little bit familiar to the fold-unfold reasoning you integrated into a separation logic-based shape domain. And I was just curious, is this related? Have you compared with this? Because also the example you had is one day verified, I believe.
So what kind of constraint does it express?
You can express sortedness, for example. You can express that you have an AVL tree, these kind of properties. And they also added a sequence or other numerical constraints on the inductive predicate.
I am not aware of this work, so I cannot answer to your question, sorry.
Okay.
Thanks for the nice talk. So I was wondering if your sequence domain could be used also in array analysis, and if you have compared your sequence domain to work that have been done in array analysis. Because it seems to be quite a natural fit.
So we looked at array abstraction from Kuzo to prove sortedness algorithm on sorting algorithm with arrays, but we noticed that the analysis is mostly based by saying that the sequence contains some distinguished variables, so inferred by the analysis with semantic criteria. And on the topic of analyzing arrays, we did not try to implement it. Sorry.
Thanks.
Thanks for the talk. So certainly verifying or analyzing sortedness is an important problem and so forth. But have you thought of other applications of the sequence abstraction combined with shapes?
So the goal of the ultimate goal of this work is to prove the preservation of invariance on a larger system, that is to say, for example, a whole scheduler of tasks, for example. So this requires also to prove constraint of sortedness, but also on the order of appearance of inserted tasks with respect to the scheduling policy, for example.
Right, yeah. Sounds good.
We have a bit of time for more questions. I can add one. So have you looked at other sequence domains and maybe consider reduced products with your sequence abstraction or those kinds of things?
So most of the sequence domains are based on regular expressions. So they are mostly tailored for word abstractions. So we may want to implement a reduced product, but a more interesting domain is the one used in this work from Boisjani and others, representing the content of K-limited graphs. It is much more expressive than our sequence domain, but it also requires the user to provide specific word patterns. So, for example, if you want to express sortedness, concatenation, or that the sequence contains the element of the Fibonacci sequence, you need to provide a specific word pattern.
Last question? Okay, if not, we can thank the speaker. Thanks. So we have a coffee break now. We start again in
to speak? Okay, all right. So it's 11 o'clock, so let's get started on the domain precision session. So we have 3 great talks coming up in this session. So people gather. All right. And also, just for anyone who's watching online, we'll monitor Discord to try to grab questions from there. All right. All right, so without further ado, let me introduce the wonderful Roberto Giacobazzi. We'll be talking about how fitting is your abstract domain.
Okay, thank you. So this is a joint work with Isabella Mastroeni and Elia Perantoni, and it deals about how the abstract domain represents the information we are considering in program analysis. So we all know that abstract interpretation is sound by construction. Okay, this is the theory. What does it mean? It means that if your specification is precisely captured by the abstract domain, imagine that the abstract domain considers circles. And what you compute are shapes of any kind. Imagine that your specification is a circle, that one in green. But what you compute is a weird shape in blue. Okay, if you abstract what you compute, you get a circle around that blue. This is not abstract interpretation, we all know. This is abstracting the concrete interpretation. Soundness means that when you make abstract interpretation, you may lose precision, but you can still prove that the semantics is contained inside the circle. That's soundness. It may well happen that it's not always complete, actually almost never complete. And when it is incomplete, it happens that during the abstract interpretation, you lose so much precision that you get out to the respect to the specification, and you produce something called false alarm. So you cannot prove what you want to prove. There are notions of completeness that are global, namely you ask to be complete for all possible inputs. This is a very restrictive case. Or it can be local. This is a relatively newer notion that we've studied about a couple of years ago, and resembles, pretty much looks like what in model checking is the SIGAR, the counterexample abstraction refinement, where you go through along the trace and you try to refine the domain with respect to that computational trace. So not with respect to all possible inputs. This is completeness. But remember that we need to use to consider this aspect. That means that the abstract domain has to be able to represent the specification. So when you consider precision, you have to consider how the abstract semantics and the abstraction of the concrete semantic relate with each other, but also how the abstract domain is able to express the information. Completeness controls the relation between the first two, namely between the abstraction of the semantics and the abstract interpretation. This is completeness. When you have equality, you are complete. When you have inequality, you have just soundness. But if the abstract domain is just I don't know, you are complete. So that produces no information at all. So you need to have an abstract domain rich enough to express the properties you want to talk about. So the loss of precision is not only, therefore, within this red arrow, but also with respect to what the abstract interpreter compute with respect to, for instance, the property of I don't know. So is the abstract interpreter able to produce something better than I don't know? That's the question. How can we model this inside the computation? We introduced the notion of adequacy, which is somehow the qualitative counterpart of a notion of partial completeness that we introduced with Mila and Marco in Popul 2022, where instead of having qualitative relation between the precision of the points in the abstract domain, so a distance, here we simply consider whether something is below the top element, which is I don't know. So if is able to produce some answer. So adequacy controls the representability and not the completeness. And indeed, we will see that the two notions are completely incomparable. Of course, you can relate with the top element, that means I don't know, and say, I want to try to prove whether my abstract interpreter will produce a better result than I don't know, okay? which is, of course, sound, but means nothing. You can play this game for top, which is I don't know, but also for any threshold you put. So you can say, well, I want to prove that my abstract interpreter is able to produce a result which is better than some given property, no matter what in the abstract domain. So the adequacy is defined in this way. Again, we have a notion of global adequacy and local adequacy. Global adequacy means that for all possible input, property in input, this is the best correct approximation. So it's the best correct possible abstract interpreter, okay? That is below the threshold, strictly. So it produces something better with respect to the precision of the lattice of abstract objects in my abstract domain. Locally, the same notion plays when you have that this has to hold for a specific input, not for all possible inputs. Look at this. Okay, in the paper, you will find other domains. You will see here the very stupid sign abstract domain, which is the usual one that we use for showing things and make them a little bit stupid. But in the paper, you will find intervals, octagons. So there are nicer abstract domains for which all this game plays in the same way. So imagine that you consider this abstract domain, which is sine. Okay, the adequacy. You will see that if you put as threshold, I don't know. So if I want to see whether with respect to that specific input, my abstract domain sine and the transfer function that multiplies by 2 is adequate, okay, whether the abstract domain sign is adequate for that specific input and that transfer function and that precision threshold, then I can easily see by computing this line that this holds. So indeed, it is adequate. Indeed, we produce something which is a point of all the positive numbers, which is strictly below all non-negative ones. This is adequate. It may well happen that this doesn't hold for all possible inputs. So it depends on the input. It depends on the transfer function. It depends on the abstract domain. You take this simple input, same transfer function, and you get that the result is definitively top. So is I don't know. This is not adequate. But look, it's complete. So in this case, the relation between the abstraction of the semantics and the abstract semantics is an equality. So that means that completeness doesn't imply adequacy. Look at this. Now you change, you keep the same input, -1, 0, and 1, but we change the transfer function. Transfer function now is n plus 2 to the square. This is non-complete, and you will see there, but it's adequate. So once again, the two relations are totally unrelated, okay? The two notions are totally unrelated. Okay, so we try to play the game, the usual game in abstract interpretation, which is, okay, we have a property, we want to achieve a goal, then we can make in two different ways, either by refining the abstract domain towards that goal or changing the program towards that goal. The second one, we didn't touch it at all. So it's probably future work, and it's some discussion in the conclusions. We did it in the domain refinement. So how to make it? It's funny and interesting that the way we make the abstract domain adequate looks pretty much the same as the way we make completeness. So we actually use the same technicalities inside the refinement. Of course, the necessary condition for being adequate for an abstract domain, a transfer function f and an input c, is that this picture holds. Namely, there is the function f applied to c is below the threshold. So what's happened? Suppose that now the refinement, as usual, and the same game plays exactly the same in completeness. We have an input refinement and an output refinement. So we can refine either by input, refining the abstraction in input, and the abstraction in output. And the two refinements need to cope. So if we want, in the end, to have one single abstract domain for both input and output, we need to iterate the refinement towards a fixed point. So what we need to add? Take the set of all points, D, okay, that are above C and have the same abstraction as C, and produce, by applying the transfer function, something that is below the threshold. Pick up one maximal element from that set, okay? That is the point, one of the points that we may add to the abstract domain. There's a problem here. There is not a unique refinement, so-called, there is not a best refinement. There are many possible refinements that produce adequacy for that domain. And this is a refinement in input. Indeed, we are producing the maximal element in input that will be mapped to something below the threshold. We can do the same in output, exactly the same structure. So what we do here is we pick up the maximal output of the threshold function, of the transfer function applied to the points that have the same abstraction in the input. And that element, which once again may not be unique, is added to the domain to become refined in adequacy. So, an example, back to the non-adequate sign domain for this little input and this transfer function. The threshold now is not anymore the top, I don't know, but is a non-negative number, any non-negative number. So what are the maximal elements to consider in input? Well, the maximal elements are there are infinitely many, any non-negative number minus one number. Okay? So I need to pick up one of them. Which one? You will see that the one that best fits to the example depends on the input. Okay? So, of course, these are the maximal elements in the set, so they satisfy the condition that the transfer function is below the threshold, and the abstraction is exactly being non-negative. We add to the abstract domain the set of non-negative minus 8. You say, why a minus 8? Well, look, look at the set in input. So it's the input that produces the way we pick up the easiest element. That abstract domain has a new point, so it's not anymore sign, but it's sign plus the fact that you may have an integer which is not negative and not 8. And then look what you compute. You abstract this set into the new domain, and you get something which is this one, this set, which is strictly below. This is not an abstract point. This is strictly below the threshold, because the threshold is being non-negative. But again, this doesn't satisfy completely the adequacy, because what's happening here is that you're becoming adequate from the input, but not for the output. So you need to iterate the refinement once again. And look what you will get now is that you add to the domain a new point, which is z minus 16, which is exactly twice 8. So we are computing in the output now the transfer function. And now what you get is exactly an adequate abstract domain. Look, the new point here that is produced here is because the abstract domain is a Moore family. So whenever you have 2 points, you have the conjunction of the 2 points, and you produce new elements in the abstract domain. And this will become adequate. So the refinement is an iteration of refining input, output, and until you've reached a fixed point. Of course, the way you pick up the elements depends strictly on the input from which you want to be adequate. I conclude with a simple program logic. So now, I mean, if you want a paper to be accepted, you have to have a program logic inside. So we made it, and we pick up a very simple syntax. The simple syntax is regular expressions. So this expresses very well the structure of contour flow graphs. The abstract semantics is made in the most simple way. This is the most straightforward abstract semantics. It simply takes the best correct approximation of the basic expressions and then compose them. Of course, the abstract semantics is not the best correct approximation, because compositionality is not preserving best correct approximation property. So this is the best semantics, the best simple semantics you can build inductively on that syntax. And then we define triples. The triple is this. It says, well, we can prove in the proof system this triple, meaning that the abstract semantics of the input assertions C produce something that is below the abstraction of the post-condition D. And that is below the threshold. So all this is below. Basically, if we are able to prove that triple, it means that the abstract interpreter will be surely below the threshold, therefore will surely produce a better result than the threshold I'm saying. Okay, and that's the rules, that's the logic. In the paper, you will find all the theorems and the proofs that justify that this proof system is sound, but not complete, of course. I just want to point out that there is an interesting rule that is exactly the copycat of a rule that we used in the program logic for local completeness, which is the so-called relax rule. The relax rule says that you can always relax the input assertion, so it goes the other way around with respect to the traditional logic. You can always relax the input assertion up to, you have to be sure that you are in the bound of the abstraction. So you are in something that will be mapped to the same abstract element, which is this one, gamma alpha C prime. And you can shrink the postcondition. But you need to be inside the same set of elements that are mapped by the abstract domain into the same point. It's interesting because the two notions are completely unrelated, completeness and adequacy, but the proof system looks pretty much the same. Why? I have no idea. Okay, okay, that's very simple. Then, for instance, we want to prove this triple. Okay, and well, basic assertions, we can prove that these two holds, namely, these are the basic assertions, so the basic expressions in my language. And therefore, we can prove this. Then by composition, we go on. And in the end, we are able to prove that the postcondition is exactly Z equals 0. And that is below the threshold. Conclusions. So adequacy can be used. I mean, the fact that it's useful is another story, but can be used, can be used to prove whether my abstract interpreter truly incorporates something, an information that is better than the threshold I'm considering. So it somehow is a kind of quality measure of my abstract interpreter with respect to a threshold that I want to consider. So if I build an abstract interpreter, I want to have some limit of precision. I fix that limit. I have a proof system that tells me whether my abstract interpreter will satisfy that limit. More interesting is that adequacy as completeness is a totally intentional notion. It depends on the way programs are written. Why this? Because the abstract interpreter, the result of the abstract interpreter depends on the way the program is written. You can write the code in two different ways, producing the same result, but having completely different abstract interpretations. So it's an intentional notion. So the question is, can we now in the paper we transformed the abstract domains to achieve adequacy, but the question, can we transform programs to achieve adequacy? That means that I better fit my code to my abstract interpreter instead of fitting the abstract interpreter to the code, which is abstraction refinement. The second one is that, actually, the second one is the one I just said. The first one is this one. Whether I transform the code in such a way that my abstract interpreter becomes inadequate. And that is exactly code obfuscation in the end. Is once again a way on which I transform my code, and in the end, my abstract interpreter produces, I don't know, as a result. Namely, is unable to extract any useful information. Thanks.
10 minutes for questions. Plenty of time.
That was a very interesting talk.
Thank
I don't know if you will roll your eyes at this, Roberto, because it's about a use, but the notion of adequacy seems to be related to the concept of widening up to. So when you do widening up to, you have like an invariant that you're trying to discharge, but your default widening is not strong enough to discharge that invariant. So you do this on-the-fly refinement of your widening, which is a bit like your threshold refinement. But in that CAV paper, there was no notion of this iterative technique.
Totally agree with you. Yeah.
Oh, okay, fine. Thank you.
I mean, you can't. I think that the same technique. I mean, somehow this is made on the abstract domain in standard Galois connection, but I think you can play this similar game in the widening.
Yeah.
And you adjust the widening to thresholds, and you see whether you can do that, up to what limit you can do that.
Yeah. Okay, cool. Thank you.
Other questions?
Very good talk. So my understanding is that you refine the abstract domain, like for instance when you went from sign to sign prime to sign double prime. My question is more about what are the what's the advantage of refining the abstract domain versus just trying to develop like more precise abstract transformers, but in a simpler abstract domain in order to like kind of attain the precision that you're
That's exactly the question I raised in the end. Changing the predicate transformer somehow is driven by the code.
Okay.
So that's what is lacking in the paper is exactly your question.
Okay.
I think it would be very interesting to develop a completely symmetric approach where instead of changing the abstract domain, so you keep the abstract domain very simple as possible, and you try to morph the code and therefore the transfer function in order to fit that.
Right.
That's actually we did that and we are doing that. Actually, is now starting a project in my university exactly in this specific case for completeness.
Okay.
For adequacy, I don't know. It's something to be done.
But great talk. Thank you.
Thank you.
Other questions? Got a little bit more time.
Okay.
Okay, I'll ask one then. I think I may have just missed this or something, but like, what guarantees that your refinement process terminates?
Oh, in the end, you may boil down into the concrete domain. So,
so not necessarily. Or?
Not necessarily. Well, in principle, yes, it may happen. You can stop whenever you want. I mean, right. you fix an amount, a percentage of adequacy of your abstract domain with respect to your input, and then you stop there. It's important the way you pick up the elements in order to reach the limit, because in the case of completeness, you have a complete share. So you have the best possible refinement in the global case. In the local case, no, there are many possibilities. And in the adequacy, it's exactly as in the local case. You have many possibilities to reach. So that's a fixed point strategy that has to be completely studied from scratch because we didn't know at the moment.
So how difficult would be to automate this procedure? I mean, checking adequacy or inadequacy?
I think it's difficult. I mean, the impression, Elia Perantoni tried to make, he made an implementation of that, pretty toy implementation where it was running on simple abstract domains, signed intervals, we'd stop it there. It was okay, but I think the way you pick up, I mean, it has to be assisted by the user because you have to provide some knowledge. Then I don't know if a large language model eventually will produce some good result in picking up the right points from the concrete domain, maybe. Okay.
Others? Okay, double check the online again. All right. Okay.
Okay.
Well, with that,
thank you.
Thank you, Roberto. All right.
Great.
Okay. All right. So our next talk is by Michele Pasqua on domain precision and Galois connectionless abstract interpretation. So take it away.
Thank you for the introduction. In this talk, I want to give you an idea on how we can check precision in abstract interpretation, for instance, by using static analysis, and how we can do it for Galois connectionless domains. So domains that are not connected by Galois connections, they are not defined on Galois connection, that are used in practice. But before that, I want to give you an introduction of the problem and the motivation. I don't know if you see my pointer. I don't have Roberto's nice fancy pointer, but so software is everywhere. So we have IoT devices all around, spread all around the world. We use programs in healthcare systems, in airplanes, and of course, programs may be buggy, and especially in safety-critical systems, this is a problem because. Oh, sorry. Okay. And bugs in safety-critical application may harm human life, so there is an ever-increasing need for correctness, for methodologies and tools to check correctness of programs. And of course, we want to check the correctness of programs as early as possible, hopefully before production. For instance, we can use testing to check the correctness of programs, but for instance, in safety-critical applications, we want something more. We want correctness proof. So we want to distill a mathematical proof that says that our program is correct. And so in some program analysis, we want to build these objects, the analyzer that takes a specification that basically say what does it mean to be correct, and takes a program and output, do some computation here, and output, yes, the program is correct, or no, the program is not correct. Of course, this object does not exist in general, because we have some mathematical limitations, and the analyzer usually can only provide the proofs for correct programs, or it says, I don't know, I'm not able to show you a proof for the program. But this not implies that the program is incorrect. And the one problem of sound program analysis is false alarms. So we have a correct programs that is marked as incorrect by the analyzer. So we have a false alarm. And false alarms are a problem because we cannot fully trust the analyzer if the analyzer outputs a huge amount of false alarms. So it is not useful in practice. And in some program analysis, you very often use abstract interpretation in order to define your analyzer. So in abstract interpretation, you have the concrete domain where programs live, and where we want to check the correctness. We want to prove the correctness of our programs, but this is a quite complicated mathematical object. So we have this other more simpler domain when we can prove we can prove the correctness of programs in an abstract way. And the concrete and the abstract domain are linked by Galois connections. Basically, we want to mimic the concrete computation in the abstract world, and because in the concrete domain we are not able to compute the semantics of our programs, so we jump in the abstract, we compute program semantics in the abstract domain. We are able to, hopefully, compute this object, and then we can prove this decidable check. So we have this decidable check that basically say that the abstract semantics imply the abstract specification we want to prove, and this implies the concrete undecidable problem we want to prove. Of course, this is a simple implication, so we have false alarms. And basically, the analyzer computes the abstract semantics. Of course, here, as also Roberto said before, we have two sources of false alarms. We have one source that is the abstract domain, so how much abstract is the abstract domain, and the abstract computation. So we have two sources of imprecision, let's say. And this is, of course, unavoidable unless we change the domain, but we can check the imprecision of the abstract computation. This is a classic notion of completeness. So completeness basically says that we don't have a precision loss in the abstract computation, and it is defined on these commutations here. So if we compute in the concrete domain and then we jump in the abstract, or it is the same as first jumping in the abstract domain and then computing the abstract function. So we don't have a precision loss in the abstract computation. This is the toy example that Roberto used, but it's the simpler sign domain. We have the abstract transfer function for the multiplication, and we all know that the multiplication is complete for the sign domain. So 1 times 2 is 2. That is abstract to positive. Positive rule of sign positive multiplied by positive is positive. So we have completeness, and we can do the same for other example. And OK, the multiplication is complete. We cannot do the same for the addition. Indeed, the addition is not complete for the sign domain. Here we have +1 that is abstracted to positive, but here negative plus positive, it is I don't know, because we have positive and negative integers. So this equation does not hold, and we have incompleteness. So this is not complete for the addition. And this is a running example, so this is, we show in some slides why I choose this domain. So the goal of this topic, of this talk, is to show you how we can check completeness or domain precision by using static analysis. So we have the analyzer that maybe compute the sign. We have a bunch of programs, and this analyzer say, yes, this program is correct, or I don't know. Some of these I don't know are indeed false alarms, and some of these false alarms are due to incompleteness of the abstract computation. So we want to ask for which program is the analyzer complete, and this is basically as this Popple paper say that we have to analyze the analyzer. So we want to analyze the analysis itself. This is quite complicated. And the second question is, can we reason about completeness when we don't have the Galois connection we have seen before between the abstract and the concrete domains? For instance, if we have affine inequalities or automata domains that are not linked by Galois connections. And I'll start by inspecting this second part, the second question. So in the standard classical setting of abstract interpretation, we have a Galois connection between the concrete and the abstract domain. Then this means that gamma is coadditive, so is meat preserving. But what does it mean? So this means that, well, of course, gamma is monotone to preserve soundness. But having a gamma coadditive, or having a Galois connection, means that for each concrete object, we can pick up a best correct approximation of this object. So we have two conditions. For each concrete element, we can derive a sound abstraction, And for each concrete element, we can find the best one. But in some cases, we don't have the best abstraction. For instance, the automata domain, we cannot approximate a context-free language with a unique regular language. And so in this case, we cannot reason about, for instance, completeness or other properties of the domain. But we can still define an abstraction. Indeed, these domains are used in practice. In this case, gamma is not more coadditive, okay? But of course, it must be monotone. But which is the requirement that we must not lose. So we must not lose the requirement that we need a correct approximation of each concrete element. So for instance, here we can map C to this point here. And the abstraction is sound. But we can map this other object in this other element. And we preserve soundness. But we lose monotonicity of the abstraction. And this is a crucial point because the only requirement, the most important requirement we can relax going to from standard Galois connection to weak Galois connection that we define is that we may relax the monotonicity of the abstraction. So we only require soundness for each concrete element, but we don't require we can relax the requirement of having a best abstraction. And this means that we can relax the monotonicity of alpha. And we will use this for next result. So we have an example here. Usually we use these examples, to say, oh, this is a bad domain. Oh, you don't do the sign in this way. And actually, it is true. It's not a domain in the classical sense, but it is a good example for weak domain. Of course, here we map gamma in this way, in the most intuitive way, and it is monotone, okay? But how we abstract 0? In this case, we have two options. We can map 0 to this guy or to this guy, but there is no best one. We cannot pick the best abstraction for 0. So in this case, we have a family of abstract functions we can use, and how we select this function or how we select the weak domains is crucial in developing an analyzer. And they are not monotone, of course. But can we still reason about these domains? Yes, we can try it. So this is the transfer function, the abstract function for the multiplication that was complete for the sine domain. And it turns out that if we choose this alpha 1 here, then we lose completeness for the multiplication. Okay, this example works, this other example works. But here, if we multiply -1 times 0, we obtain, of course, 0, that is mapped to positive. But here, we have negative times 0, that is mapped to positive. So negative times positive rule of sign is negative. So we lose completeness for the multiplication. But instead, if we select the other option, then we still we maintain completeness for the multiplication because now this guy is mapped to to negative, and we have completeness. So we have a way to select a best weak domain in order to satisfy, for instance, completeness. Or we may change the domain at runtime when we run our analysis. And we started investigating from a theoretical point of view weak closure, so weak abstract domain, as we do in the classical setting. And when, of course, we reduce Galois connection to a Galois insertion by making gamma injective. So in the weak abstract interpretation framework, let's say, so weak domains, when we maintain the extensivity of gamma after alpha, and we maintain idempotence. But we lose again monotonicity. So the only difference between weak domains and non-weak domains or domains is the lack of monotonicity. And this is helpful, very helpful, because we can reuse techniques, construction proofs that we use for standard domains in the weak setting if we don't use monotonicity, for instance. So a weak closure is basically an upper closure operator that is not necessarily monotone. And we start reasoning about this stuff, but it is just initial work. Here we have two examples of weak domains. So if you can see here, we lose monotonicity. And of course, we can compare weak closures as we do with standard closures by pointwise comparison of between functions, and we may define the postset, the partially ordered set of weak abstract interpretation. We have to investigate more if maybe we can end up in a lattice or do some more technical stuff on this topic. But we have a negative result. But you can, this is indeed a counterexample. Upper closure operators can be uniquely identified by the set of their fixed points. But we cannot do the same with weak closures. Indeed, these two weak closures have the same set of fixed points, but they are different. So we lose this nice property of weak closures, of closure operators. Now let's jump to the other question. How can we derive a static analysis to check completeness? Well, completeness, as we said before, involves the abstract, the computation, so the analysis, the analyzer. Indeed, it is a property. We want to check a property of the analyzer. Indeed, this is okay. The definition of completeness written in terms of upper closure operators, and here rho after f after rho is basically the analysis, so the analyzer. So in this equation, we have the analysis, and so we have to check a property of the analysis, but this is quite difficult. Checking the analysis, the analyzer is quite difficult, so we tried a way to remove the analyzer from this equation. Can we check completeness only in terms of the program, not in terms of the analyzer? And the answer is yes, and I'll give you a very, very high-level idea. So if completeness holds, then we have that, okay, we apply the concrete function, we go in the abstracts, and we have the commutativity, so this is equal to the abstract function. But we have a universal quantification, so we can do this reasoning for another point, x2. But what happens if we impose that x1 and x2 have the same image under rho? Well, so these two elements are the same, but f is a function, so these two guys collapse. And also rho is a function, so these two guys collapse. And so basically, if we assume this equation, so if you assume that the inputs of the concrete function have the same image under rho, then we have that the abstraction of the concrete computation is the same. So we removed here the dependency on the analyzer, so we can reason about completeness only in terms of an abstraction of the concrete computation. Well, this is an hyperproperty of the program. So we jumped from a property of the analyzer to an hyperproperty of the program. I won't go into the details of hyperproperties, but a special kind of program properties that talks about the partial aspects of the computation. So for instance, if you want to check a null pointer, check a null pointer exception, you can in principle run each execution of the program, possibly infinite set of execution, but if there is a bug, just looking in isolation and on each execution, we will find a bug. So if there is a null pointer exception, looking singularly on each execution, you will find the exception, if there is one. But this is because the bug is defined in terms of single execution. But there are some more tricky bugs that requires different execution, even not only to be verified once, but to be defined. For instance, information flow, if you want to check a leak, information leak, you need to compare different program execution, or in concurrency requirements. You cannot even define data arrays if you only have one execution. So with hyperproperty, we can model this kind of requirements. And to verify the hyperproperties, we want to look at partially on the semantics of the program. So we have to analyze each subset, in principle, of the semantics of the program. But we can do it with static analysis. We prove it. But which kind of hyperproperty is completeness? If indeed here we have a very common pattern if you work in language-based security, and this is indeed non-interference. So this is okay. We have two different domains in input and output. But you can replace eta with raw, and everything works. And indeed, abstract non-interference basically says that if we have two inputs that are equal and up to eta, and we compute the function on these inputs, then we end up into outputs that are equivalent up to rho. This is a generalization of the Cohen and classic non-interference, but this is exactly the definition of completeness we have seen before. And indeed, of course, we have shown, I give you an idea of one of the implications, and we prove also the other implications. So we prove that completeness is equivalent to abstract non-interference. And this is nice because we can develop some verification mechanism. We have some verification mechanism for non-interference and abstract non-interference. You can reuse them to verify completeness. And this also works in the case of weak domains, because in all construction, in all proofs, we don't use monotonicity. But the only difference between weak domains and a standard domain is monotonicity. So we can apply the same reasoning on weak domains and check completeness also for weak domains. For instance, we can induce completeness for weak domains. Indeed, the complete shell and complete core that has been developed for completeness. I won't go into details, but we can remove some object in the abstract domain in order to achieve completeness, or this is the core, or we may add some elements in the domain to achieve completeness. This is the shell. And these core and shell have been developed in terms of abstract interference. So we can adapt this construction and definition to the weak domain settings. And indeed, we provide in the paper a deductive system for abstract interference on weak domains. That is a slight modification of the one that has been developed for classic abstract interference in 2010. And so we can derive inductively on P syntax, in the program syntax, the most abstract domain such that completeness holds for the program with this deductive system. But we can do more. We can statically verify completeness, even for weak domains, by using hyperanalysis. So for non-interference, classic non-interference has been developed a static analysis that based on hypersemantics, so that verifies non-interference. I won't go into details, but we need hypersemantics that computes on set of executions in order to model partial aspects of the semantics of the program. Then we need a suitable hyperdomain, so a domain defined on a set of execution, and then we can verify no interference. With a slight modification, we can do the same for abstract interference, and so we prove that we can build a static analyzer that works, that verify abstract non-interference, and in turn that it can verify completeness. So we can build this static analyzer and check non-interference, abstract non-interference, and in turn completeness for a given program. Of course, we have a false positive also in this case. So to conclude, we basically restated the problem of analyzing an analyzer. So is the analysis for P complete? With a more simpler question, is P is abstract non-interference? So we jump from a property of the analyzer to a hyperproperty of the program. So we can verify a property of the analyzer only in terms of the program. This is much more simpler. And we can do it by extant interpretation. And so we can derive an hyperanalysis for P. So we can build an effective verifier for completeness by exploiting the correspondence between completeness and abstract interpretation. And we can do it also for weak domains. So restating Jacobazzi et al. In this paper, completeness is an hyperproperty of the program. And of course, a property of the analyzer. And as a future work, we can extend this finding to other flavors of completeness. For instance, we have the classical notion of completeness, which is global, and so Roberto said before, we can check a local version of completeness when we require the commutativity here only for some points of the domain, not for all. And we can also, we have partial completeness when we relax the equality here, and we allow a little information loss, but this imprecision is bounded by a given epsilon here. And we can formulate all of them as hyperproperties. So in principle, we can verify all these property of the analysis on the program with a hyperanalysis. And this works also in the weak domains case. So we can statically check the precision of a static analysis. We can prove it for completeness, global completeness, by using an hyperanalysis for abstract interference. We are pretty sure that we can do the same with local completeness, because we just have to tune the hyperanalysis to select on which point we can start the abstract computation. And we believe that we can also do the same for partial completeness by using, instead of abstract interference, the quantitative version of abstract interference. So abstract interference basically say there is or there is not a leak, information leak. In the quantitative version, we measure how much information is leaked. So for instance, if we leak 1 bit of a password, maybe okay or maybe not. But we can bound this information leak. And it's quite related to partial completeness. So we believe that an hyperanalysis for quantitative ANI can be used to check, statically check partial completeness. And everything works in the weak domains. Again, because in all construction, in all proofs, we don't use monotonicity. as a long-term view, can we generalize the approach to any other analyzer property? If there are any other interesting analyzer properties, we don't know, but probably yes. And we are working on that. So thanks for the attention, and if you have questions.
Questions? Time for a little bit of time.
I'm sorry for the baby screaming. And I'm also sorry for the formulation of the question. I'm not sure I do it in the right way. But so when you talk about completeness, this is for safety property, right? So what I'm getting at is, what if the property that you're interested in is non-interference? Can you do completeness of non-interference with non-interference?
Yeah,
kind of
this
thing?
additional level of abstraction, let's say. We didn't investigate this problem, but in principle, yes. And this, but we have to investigate more this topic. But it's quite interesting because also the upper analysis can have false alarm, so we can check completeness also for the analysis of the analysis. So.
Okay, thanks.
It's better. Other questions? Double check online here. Nope. All right, I guess I'll ask one. I don't know if I just missed this, but like when you're trying to, with these weak abstract domains, do you have to do this kind of domain by domain analysis to figure out, which abstraction to use and so forth, and to get completeness?
Yes, if you want to check completeness, you have to focus on a given analysis. So yes, you have to. Also, in the case of weak domains, you have to focus on a single domain. Yeah.
So like in the example you gave with just the weak sign, just for simplicity, right? Like for multiplication, one of them was complete and one of them wasn't in terms of the abstraction function choice. Can you automate that selection somehow, or is there a methodology? Or
actually not. We don't have a methodology or an idea how we can automate this process, but yes, for now it's totally manual. But you can insert a heuristic that force, I don't know, completeness. If you know your program, you know maybe in the program you have a lot of multiplication, then we can use this alpha, but you have to analyze your domain, your weak domains before. Yeah.
All right, let's thank the speaker. Last speaker of the session. All right, so our last speaker of the session is Marco Campion, who's going to tell us about a formal framework to measure the incompleteness of abstract interpretations. So take it away.
Okay, thank you for the introduction. This is a joint work with Caterina Urban from INRIA, Mira Dalla Preda from University of Verona, and Roberto Giacobazzi from University of Arizona. So in this talk, I'm going to formalize the minimum requirements that a distance function should meet in order to measure the incompleteness of abstract interpretation. So again, we are speaking about completeness and its weakening. It is the partial completeness in this case. So just a bit of background before. What is the key idea of abstract interpretation? In this case, the key idea is to provide an approximation. So replace the computation of concrete operators over undecidable properties by abstract operators over approximated decidable properties. for our purposes, we are just requiring a very small structure between the concrete properties and the abstract properties. So we require at least an ordering, which is a pre-order, and a concretization function from the abstract properties to the concrete properties. So it might also not enjoy the Galois connection. So when an abstract operator is sound, then an abstract operator is sound when is a sound approximation of a concrete operator when the concretization of the result of the abstract operator is always an approximation of the result of the concrete operator over all possible abstract inputs. So the best possible scenario is when this inequality becomes an equality. And in this case, we get the so-called forward completeness, so the completeness over the concrete properties. Namely, the abstract operator is forward complete for all possible abstract inputs. We can require also a weaker version of forward completeness, which is called the local forward completeness, when we require completeness over just an input. So in this case, it might happen that the result is not the same in the concrete properties. So when concretized, when the result of the abstract operator is concretized over the concrete properties. So in this case, we have a forward incompleteness. When the concrete properties and abstract properties enjoy a Galois connection, so through an abstraction function, then in this case, we can formalize the well-known backward completeness properties, which is the property that was in the previous talks. And this property says that an abstract operator is backward complete for respect to a concrete operator for all possible concrete inputs in this case, when the result of the abstract operator is the same as the result of the abstraction of the result of the concrete operator in this case. And also, again, we have the local version. So we say that is local backward complete for a concrete input when the equality holds for that input. So it might happen that it is backward incomplete for a concrete input. It has been proved that this property, when used to prove program property, when used to verify program properties, is very hard to achieve or even impossible, also for the local version, for the backward completeness. So that's why in the POPL 2022, it has been introduced the partial backward completeness, which is a weakening of the backward completeness property, namely of the local backward completeness property, because we are requiring, so we allow incompleteness over the result of the abstract operator and the concretization of the concrete operator, but we require that this difference is limited to an epsilon amount, which is measured by a quasi-metric distance. And these are the axioms that define the quasi-metric in this case that we will see better later. So for example, as a quasi-metric distance, which measure in this case, the incompleteness over the interval abstract domain, we can define the weighted path length that sees the interval abstract domain as a graph, as a directed graph in this case, is a weighted directed graph, where we have the weight over each edge. And in this case, the distance is simply the minimum weighting path between two comparable elements. So for example, the distance between the interval 0, 0 and the interval -1, 2 is 3, meaning that there are 3 mole discrete elements between these two intervals. It is undefined for non-comparable elements. And it is infinite if, of course, there are infinite more elements between two comparable intervals. So note that in this case, the quasi-metric here defined, the weighted path length, satisfies this if and only if. Namely, whenever the distance returns 0, then we are sure that the two elements that we are comparing are equal. So now I want to show you why it is limiting to use quasi-metric to measure incompleteness. Well, let's start by analyzing the axioms of the quasi-matrix. So the first axiom requires that the distance function should return a value only on comparable elements, but in this case, it's not really necessary because we can even allow the distance to return any value on all elements, even on uncomparable ones, because actually we are using this distance function to measure the distance between two comparable elements, because we are measuring the distance between the result of the concrete and the abstract analysis, which by assumption is sound. So they are always on the same chain. And the second axiom in this case is really too strong, because here this axiom is requiring the distance function to adhere precisely the underlying ordering, namely to return 0 every time we are measuring the distance of the same element. But in this case, the left implication is too strong, because maybe we are interested in formalizing a distance which is an approximation, which is approximating the computation of the distance between two elements. So in this case, the distance maybe even return 0 on two elements that are equal, because the distance itself is seeing the two elements that are in fact equal. So for example, suppose that we want to define a distance on the concrete properties in this case, and we don't have a Gola connection, for example, on convex polyhedra. And in this case, we are forced to define a distance that recognizes when two elements are equal. So it must study all the information inside the concrete elements. So we are not allowed to define distance which approximate the computation. And also the last axiom, which is the triangle inequality over chains, is not really necessary. So we are now formalizing a new distance function, which require just an ordering over our set of properties, which it is at least a pre-order. So this is the signature of our new distance function, which always return, in sense, it is a matrix. It must be a matrix, so it always return a value. And this is the only requirement about the metric that we require, so only the right implication. When the two elements are equal, then the distance must be 0. But it might not be the case with the left implication. And in the literature, these two axioms define what is called a pre-metric in this case. So we need a sort of compatible axiom over the ordering. So what we are requiring for the distance function is that when we are measuring the distance between elements of the same chain, then we require that the distance between, say, x and z is always greater or equal than the distance between any elements in the middle. So this is the only requirement that we ask for respecting the ordering in this case. So when a distance function satisfies these two axioms, then we say that this is a pre-metric compatible with the pre-order relation of our domain. For example, the weighted path length that we have defined before is a pre-metric compatible on the interval abstraction. But we can even define another pre-metric here. Suppose that our elements is a vector of intervals, and we can define in this case a metric that is interested in measure just the distance between only one component of that vector, for example, the I component. So in this case, we are using the weighted path length for measuring that single component. And this is a pre-metric compatible with this domain. And note that this is not a quasi-metric, because the distance in this case is measuring just the distance between two single intervals and not all the vector. So it might be the case that the distance is 0, but the two vectors are not the same. So as another example, suppose that we want to define a distance over the convex polyhedra domain. So in this case, we can define, for example, the distance between two polyhedra as the absolute value of the difference between their volume, where vol in this case is a volume function that calculates the volume. This is a pre-metric compatible with the convex polyhedra domain. And here, thanks to the thanks to the few axioms that require the pre-metric, we can even over-approximate the real volume here with this metric. So this may not be a quasi-metric. So now we can use the structure of pre-matrix to derive also pre-matrix from between domains. So suppose that we have the concrete properties and abstract properties are just, they share a concretization function. We don't have a, oops, sorry. Let's stop the presentation. So we don't have a Gola connection in the left case, but we have defined a distance on the concrete properties. Well, in this case, we can derive another distance on the abstract property by using the concretization function, and this distance is still a pre-metric compatible. Of course, it's measuring something which is approximate. So, for example, we can reuse the same metric from polyhedra to calculate the volume of other representable abstraction like octagons or intervals. We can do the same also when we enjoy there is an Galois connection between two domains. So we can, from a distance defined on the abstract properties, we can derive the distance on the concrete properties by using the abstraction function. And this is still a pre-metric. So we can now define a revised version of our partial completeness properties. So the partial backward completeness properties now uses this definition of pre-metric. But we can also now define the epsilon partial forward completeness properties, because we can now define also distances of the concrete properties. So we can say that the abstract operator is epsilon partial forward complete when the distance between the result on the concrete properties, between the abstract and the concrete operators is at maximum epsilon. And here, again, we are using the pre-metric compatible over the concrete properties. So as a last very simple example, we just show how we want to verify the epsilon partial forward completeness on this small program. So here we are using the interproc static analyzer to infer the loop invariant of this program. And we are using the abstract domain of octagons and polyhedra. We want to measure the incompleteness in this case using this pre-matrix. So what is the calculation of this metric, of this pre-metric? Well, we are calculating the Moore volume that has the result of the abstract interpreter with respect to the result of the concrete interpreter. So this is the percentage of Moore volume that has the result of the interproc static analysis with respect to the concrete analysis, just as an example. So we are asking whether the result of interproc using polyhedra and octagons is 20 partial forward complete. Namely, whether the imprecision injected by interproc, the percentage of imprecision injected is no more than 20%. And this pre-metric actually is computing the volume using an approximation because we are calculating actually the volume of rectangles. So we are applying another level of approximation. We are considering the result. We are approximating the result as rectangles, so we are calculating the volume of rectangles. So the computation is much faster in this case, without computing the exact volumes on polyhedra. So for example, these are the results. These are the invariants generated by interproc, with the octagons on the left and polyhedra on the right. These are what the pre-metric is computing. So it is taking their approximation over rectangles, so over intervals, actually, over boxes. And this is the result between those two. So it actually says that the result of the octagons analysis has approximated 33% more volume than the result of the polyhedra analysis in this case. And similarly, the result between the polyhedra analysis and the concrete analysis is 20%, as an inaccuracy of 20%, while between the octagons and the concrete analysis is 60% more. So we can conclude that the analysis of interproc over polyhedra satisfies our properties, which is the 20 partial formal completeness for all inputs in this case. but the octagons analysis does not satisfy this property because it has more inaccuracy in this case. Just an observation here, we can also characterize the local forward and backward completeness when our pre-matrix that we have defined satisfy this axiom, namely it can recognize the equal elements only on comparable elements. Then we say that in this case the pre-matrix is strong. So for example, the weighted Paulin, which is also a quasi-matrix, of course is strong, while the matrix with the pre-matrix that we had defined before is not strong because it approximates the result by computing the volume of rectangles. So it may calculate the distance 0 even if the two elements are not the same. So in this case, we have two theorems. So if we had defined a distance over the concrete properties, which is actually strong, then if we are able to prove that our abstract operator is 0 partial forward complete over an input, then we can say that is also locally forward complete, and vice versa. And if you have defined also a distance over the if we have defined a distance over the abstract property, and this distance is strong in this case, then we can say that if we are able to prove the 0 partial backward completeness over an input, then we are sure that we are also locally backward complete, and vice versa. So why it matters? So why it is important to study this kind of matrix? Well, this is because we must be sure that what we are using to measure the incompleteness, so the imprecision of our analysis, must satisfy at least a few axioms to be used to have a meaning in this case. So we should define a distance that it is measuring what we are interested in order to control, for example, the incompleteness propagation, maybe because we have to check how we have designed the abstract interpreter. And also, thanks to the very few axioms that require the pre-matrix, we can derive and combine pre-matrix, derive from other domains and combine pre-matrix that we have already defined. And this could be also a way to measure, for example, the potency of code obfuscation techniques when used to obfuscate the analysis, to worsen the analysis in the case. And that's it. Thank you.
We have time for questions. Quite a bit of time. Don't be shy. All right, I'll ask one to kick it off. So I guess you gave some good intuitions for this measurement when you're in terms of volume for numerical abstract domains, and I kind of see that. I have no idea what that would look like for something symbolic, like separation logic domains or something like this. So I don't know if you have any thoughts.
So I didn't understand the question.
So all your definitions in these metrics make sense from a numerical domain context,
yes.
Right? In terms of measuring volume and the differences between octagons.
Yes. Okay. So actually, we have defined the examples that we have provided in the paper are most of them numerical. Actually, we have also an example over a very simple concrete domain like the set of traces in this case. But our idea was actually to just give the axioms on what we have to satisfy in order to define any kind of distance that measure the incompleteness over any domain of properties in this case. So even non-numerical properties. Okay.
Can you give a little bit of intuition of that for non-numerical ones?
Okay. For example, if we are considering, for example, I don't know, the set of traces, for example, we can define just as a measure between the result of the abstract analysis and the concrete analysis, for example, just to measure how many more spurious traces that we have between these two results. And this is still a pre-matrix in this case.
Mm-hmm. Okay, thanks. Yeah. All right.
So how do you calculate the distances manually using pen and pencil or automatically?
Well, in our paper, we just did it manually. So we didn't implement it any distance. We did just a theoretical formalization in this case. So, but the idea is that usually when someone is designing an analysis, a static analyzer, at some point he must it must be controlled the incompleteness in this case. So at some point you have to define an evaluation. So how many, for example, false alarm your analysis has generated. So in a sense, you are defining a pre-metric in this case.
Other questions? Check online. Yep. All right. Okay. Can we close the session then? All right. Thank you.
Thank you.
All right. Hello, everyone. Welcome to the session at SAS on program synthesis and applications. And first, as the first speaker, we have Alexander Dimowski, who's going to tell us about program sketching using abstract interpretation. Take it away.
Can you zoom it? Full screen zoom?
If you want to present. Oh. Click F5 on your presentation.
Okay, so thank you. So I'm Alexander Dimovsky, and I will be talking about generalized program sketching by abstract interpretation and logical abduction. So sketch is a partial program with some missing expressions called holes in it. The standard sketching problem, as addressed by the well-known sketch tool, is looking for synthesizing integer constants for the holes so that the resulting complete program satisfies all assertions in it. In this work, we are taking a more challenging task, and we consider so-called generalized sketching problem, where we want to find arbitrary expressions instead of integer constants for the holes. To solve this generalized sketching problem, we use abstract interpretation and logical abduction. To be more precise, we use forward static analysis to compute invariant or premise P at the location before the unknown hole. After that, we use backward static analysis to compute sufficient condition or conclusion C at the location after the unknown hole. And this sufficient condition is such that the code after the hole will satisfy all assertions in the program. Then we use abduction in order to generate explanation E formula such that premise P and E, explanation E imply the conclusion C, and at the same time the premise P and explanation E do not contradict each other. Once we find this explanation formula, we will infer from it a concrete expression for the whole. So let's see our approach through several introductory examples. In this example, whole occurs as an arithmetic expression in an assignment. Then we use forward analysis in order to compute, we use forward polyhedra analysis to compute the premise at the location before, at the location 3 before the unknown hole. Then we use backward static analysis to compute sufficient condition at the location 4 after the hole. After that, we generate one abduction query which says that the premise in which we rename the variable epsilon to epsilon prime. So the abduction query says that the premise and the unknown predicate are defined over all program variables at the scope of location 3 will imply the conclusion C. Now, among all the solutions of this abduction query, we are looking for the one that, we prefer the one that contains variable epsilon. And the solution we obtain is this one. And this solution represents the weakest possible specification for the unknown, for the statement at location 3. So from this specification, we infer one possible concrete expression, in this case, that is epsilon plus 1. Of course, other concrete expression will be okay as well. For example, epsilon minus 1, epsilon minus 2, etc. Let's consider another example. This example computes absolute value of an integer. And here the unknown whole is if guard. So using forward analysis, we compute the premise at location 2. Using the backward analysis, now we compute two sufficient conditions at the beginning of then and else branches. And using these facts, we construct two abduction queries. In the first query, the unknown predicate is R true. In the second query, unknown predicate is R false. By solving these two abduction queries, we obtain concrete predicates for R true and R false. And now we are checking whether negation R true implies R false. This implication can be checked using an SMT solver. And if this is, in this case, this is correct, so we can return the predicate n less equals 0 as a solution to this sketching problem. So we can substitute it at the place of unknown whole. In case this implication does not hold, we have to strengthen our true predicate in order to obtain this implication to be valid. And the third example uses unknown whole as a wild card. So in this case, using forward analysis, we compute premise or invariant at the guard location. Then using backward analysis, we compute sufficient condition at the location after the wild card. Then we generate abduction query where the unknown predicate is R false. By solving this query, we obtain the result x equals 0. Then R true will be negation of R false. In order to obtain more precise wild card, we are performing two additional backward analyses. The first one for the sketch where wild card is x less than 0 and whole 1. The second one for the sketch where the wild card is x greater than 0 and whole 2. Then we calculate sufficient preconditions at location 3. We generate two abduction queries, and from them we obtain that whole 1 is false and whole 2 is true. So we can infer the predicate x greater than 0 for the wild card. Now we can state the contributions of our work. So we define the generalized sketching problem for synthesizing arbitrary expressions for holes in program sketches. Then we present a solution to this problem by using abstract interpretation and logical abduction. Then we built a prototype synthesizer, which is using static analysis tools based on abstract interpretation and logical abduction solver. And then we evaluate it on several numerical C programs. The language we consider is a simple C-like language extended with whole constructs. As we can see, the whole can occur as arithmetic expression in assignments and as Boolean expression in if and while guards. Then we assume that a program is a sequence of states followed by one assertion. Then we define a control function as a mapping from the set of all holes to concrete expression. And we say that one control function is complete if it is defined for all holes. Otherwise, we say that phi is partial. Then we define a program P of phi, which is the program obtained by substituting each hole in P with the concrete expression as defined by control function phi. Then we say that one complete control function phi is a solution to the sketch P if the complete program P of phi satisfies all assertions in it. The concrete semantics of the language is defined using the concrete domain of power sets of memory stores. The forward invariance semantics finds all possible reachable stores at all locations in the program, while the sufficient condition backward analysis finds a set of possible stores from which a given post-condition must be reached. So this post-condition is given in a form of a set of stores S capital. So we all know that this language is Turing complete, so the concrete semantics cannot be computed. That's why we are using abstract semantics, which is defined over abstract numerical domain D, such that there exists a concretization-based abstraction between the concrete and abstract domain. Then we define abstract invariance semantics, which over-approximates the concrete one, and we define abstract sufficient condition analysis, which under-approximates the concrete one. And now we define the abduction problem as a formula. Rx and P implies C, where Rx is an unknown predicate defined over a set of variables X. P is the premise, and C is the conclusion. And one solution is a formula phi, such that phi and P implies C, and phi and P do not contradict each other. And then there exists a procedure abduce that solves this abduction problem as implemented in the explain tool. Now we present the synthesis algorithm for solving the generalized sketching problem. So the inputs are a sketch and a set of holes in it. Then we use one iteration where for each hole in the sketch, we first extract the statement where the hole occurs. After that, we call the special function solve for solving sketches that contain only one hole. After obtaining the corresponding expression E, then we update the control function phi using the found entry. Now, when we fix one hole, in that case, all other holes are treated as non-deterministic choices over arithmetic or Boolean expressions. So in order to obtain more precise results, we are performing another iteration where when we synthesize expression for one fixed hole, for all other holes, we use the expressions that are calculated in the previous iteration. So now we show the synthesis algorithm for solving one-hole sketches. So we first use forward static analysis to calculate invariance in all locations. Then if the hole occurs in assignment statement, we use backward static analysis to compute sufficient conditions at all locations. After that, we raise this abduction query. And from the solution of this abduction query, Rx predicate, we synthesize concrete expression that will be substituted for the corresponding hole in the sketch. In case that hole occurs as a if guard of if statement, if guard, in that case, again, we are calculating the sufficient condition, backward analysis, and after that, we are generating two abduction queries for the true and for the false branch of if command. And then using the found solutions for these two predicates, we again synthesize concrete expression for the if guard. And in a similar vein, we handle also the case when the unknown hole occurs as a while guard. So we have implemented our synthesis algorithm called GAN sketching in OCaml. For abstract numerical domains, we use the APRAN library. And more precisely, in our experiments, we use the polyhedra domain. And for the for solving abduction and SMT queries, we are using the Explain and Mistral tools. We compare our tool with the well-known Sketch tool, which uses SAT-based counterexample guided inductive synthesis. And we have to say that this approach handles loops by unrolling them, so its performances are very sensitive to the degree of unrolling the loops. And the other tool that we are using is Family Sketcher. It represents all possible sketch realization as a program family and then performs an efficient lifted analysis on the given program family by using specifically designed decision tree abstract domains. And some of the benchmarks that we consider are this one. So the first example finds maximum value of 3 integers. In this case, the unknown whole can be either arithmetic expression in assignment, or it can be if guard. Then the second conditional example uses contains one if guard. The unknown whole is if guard. And then we have a example that uses while loop, where the unknown whole can be either a while guard or assignment statement before the while statement. Here we are showing some performances results that compare against sketching, Sketch and Family Sketcher. So here we have to say that the Sketch and Family Sketcher are solving the standard sketching problem. So many of these examples, they cannot handle them directly. For example, if we get back to the intro example, they will solve this example only if we write at location 3 epsilon equals epsilon plus whole. So they cannot solve the generalized problem. They cannot. They can return only integer constant. They cannot return arbitrary expression. The second thing is that these two tools depend on the size. Their performances depend on the sizes of the whole. So for each whole, they explicitly define some finite domain of values that whole can have. So here we consider 2 versions of these 2 tools, where the wholes have 5 bits and 10 bits. And the third thing that, as I said before, Sketch depends on the degree of unrolling the loops. So in the cases when we have these programs with while loops, the performances of Sketch decline. So here I have to say that Sketch, being based on SAT solvers, is a more general tool than GAN sketching, in the sense that it can handle a different range of programs. It is especially suited for bit manipulating programs. On the other hand, our tool based on abstract numerical domains can handle mostly numerical programs that contain linear arithmetic, because the abduction solver can also handle this subset of first-order logic. So we can see that our tool outperforms these 2 tools in the sense of running times and also in the sense of complexity of problems. So in the end, to conclude, in this work, we employ techniques from abstract interpretation and logical abduction to automatically resolve program sketches. We present a synthesis algorithm that infers arbitrary expressions for unknown wholes. And we experimentally demonstrate the effectiveness of our approach on a set of interesting C numerical sketches. Thank you.
Thanks for a great talk. Are there any questions? If you're remote, you can post your questions on the Discord thread. If not, then I can start us off with a question. So how feasible would you say is it to extend this approach to other data types other than just integer expressions?
Yeah, but this mainly depends on the abstract domain that we have. I mean, in the background. So, I mean, if we have more efficient, I mean, different. For example, nowadays we also have bit manipulating abstract domain. And if we use that domain, we can easily construct a tool which is very similar to Sketch.
Thanks.
So it depends on the underlying abstract domain.
And what kind of data types and theories can these abduction solvers handle? You mentioned linear arithmetic. Can they also deal with like other kind of SMT theories or things like that?
Yeah, at present, that can be also a bottleneck of this approach because this explain abduction solver at this point can handle only linear arithmetic linear arithmetic first order logic. So our approach also depends on this solver.
Makes sense, thanks. Any other questions? No? Let me check online. Nope, no questions online either. So let's thank the speaker again. All right, and our next speaker is Mathieu Lemaire, who's going to tell us about reverse template processing. So please take it away.
I just put it. No, it's working, I think. Oh. Sorry, 1 minute. Yes, sorry about the delay.
So, yes. So my talk is about reverse template processing by abstract interpretation, and what it is basically about is using the standard static analysis development method, the abstract interpretation method, to a new problem. So what is a normal template processing, which is also called template evaluation? The idea is to take as an input some tree-structured data. So when I will speak about database, you have to think about JSON file or XML file. And then we have a template. So what is a template? It's a sequence of constant text with formatting directives. So this says that if in the database you have C, which is false, then you print 0. Otherwise, you print the value of X. And then you have an output text. So this is something which is very, very common. You have that, for instance, to produce HTML documents in the web. You have also XML transformers like the XSLT language. And also you can think of the C macro processor as doing this. It takes as an input some file and it outputs some C file which is preprocessed. So very, very common. So the template language takes an input and tree database, which is a kind of JSON. So in our example, we take only, so what is the database? It's either a scalar. In our example, it's either an int or a string, or it is a record, a mapping from field to a database, or a sequence of database. So this is really, really like a JSON. So for instance, this is an example document. So my name is Le Maire, and I have another field which is papers, and the papers is a list of sequences. And we have different instructions, and these are the instructions that we do handle: constant text, replacement. So basically, pass refers to somewhere in the tree. So in the tree database, we have a pass which refers to some data, and we output that data. We can concatenate some instruction. We have conditions, we have loop iterations, and we can also call sub-templates. Okay, so now what is reverse template processing? So it's basically the contrary. We take the output text, we take a template, which is the same as the one I showed you before, and then we give the input database. And there is not only one database, because template evaluation in general is not in an injective function. So there are multiple inputs that can correspond to the same output. So this is the one that we had earlier, but we can also have the case where C is true and X can have arbitrary value, or X can also not be defined here. Or you can have also other fields that are not used by the template. Basically, we have an infinite number of possible inputs that will produce the same output. And so our goal is to exactly characterize all the inputs that corresponds to some output. So why do we want to do that? This is a side note of the practical motivation for this work, and it was in the context of aeronautics certification, where some people, basically what they do is generate this parameters database in a JSON file, and then they use template processing to produce some constant source code, which is used after that in an embedded system. And for certification reasons, they want to retrieve the database. So this is where reverse template processing will take place, so that we can validate the database against soft safety requirements. So why don't we use the original database? It's because we don't want a common cause of failure. Well, this is a certification. Often it's more important to obey the letter of the rule than to the spirit of the rule, but yeah, this is how it works. But there are also a lot of other applications of reverse template processing. Basically, it allows to create a parser from a pretty printer. So some people have difficulty to write parsers, maybe some complex to the average programmer, but the template processing is to be quite easy. And it can also solve what is called the view update problem. So in this problem, you have a database, you extract some data from the database, and then the user wants to modify this data. And then the question is how you can incorporate this modified data back into the original database. And think, for instance, of a web page that outputs some data, it's modified and then replaced in the original database. So this is a problem that has been investigated quite a lot in the past.
And reverse template processing could also be a useful brick into this, to this topic. So now, why exact reverse template processing is a hard problem? First, it's a problem which is not decidable, because if you can exactly characterize a set of inputs that corresponds to an output template, then you can use that to solve, to get all the solutions to a Diophantine equation, and finding solutions of Diophantine equations is an undecidable problem. So this makes reverse template processing an undecidable problem. So the solution for this, when we have an decidable problem, is to be sound but not complete. We give up on completeness, and so either we succeed in characterizing all the possible inputs, or we fail in doing so, and we report that we failed. Another problem is that the possible inputs are infinite. So I said that you can always add more fields in the database that are not mentioned in the template. So of course this will create an infinite number of databases, but you can also have an infinite number of list elements in some case. For instance, here, I iterate on a list and I print every element in the list. So the obvious solution to correspond to the output A is to have a single element list which with the field A. But you can also add some empty elements before and after that will also belong to the list. So there are several sources of infinity. So basically what we want is we want a finite abstraction corresponding to an infinite set. So this should ring the bell that we want abstract interpretation and to have a Galois connection between a finite representation of some data and an infinite number of data. And lastly, we want precision. Precision is important, and what we will see is that we will have to incorporate a lot of specific rules to reach the required precision, and we want to do that in a principled way. And so we want a modular and semantically justified composition of different abstractions. So as I've presented this in the background of the audience, everybody should think about that abstract interpretation is a perfect fit to this quite unusual problem. But interestingly, this has not been the case in the past. If we look at related work, so this exact problem has not been investigated, but there are some very related problems, and people did not use abstract interpretation to solve it. For instance, you have some tools which do automatic conversion from pretty printers to parsers, and also that do bidirectional programming, which is techniques to handle this view update problem. And often they are limited to injective programs, which means that in the template that we use, you cannot refer to a data twice, and you have to refer sometimes to all the data, which is very, very important limitations. Basically, in the case studies that we want to handle, none of these data, none of the template would obey these restrictions. There are also solutions based on logic and constraint programming, which has a generic technique for program inversion, but they are non-terminating because they enumerate generally all the possible solutions, and we have an infinite number of them, so it cannot work here. There are also techniques for typing XML transformation using very complex abstractions like tree transducers. And I think this should be seen as an instance of abstract domains. And if you see them as abstract domains, then you can combine them with other abstractions, which can be done in the current work. So in the end, abstract interpretation will handle non-injectivity just fine. It will allow to finitely represent an infinite set and so guarantee termination. And it will allow combination of abstractions. So it's interesting that nobody tried it before. So how will this work? The first idea is that if you see a template, the template is a kind of specific expression. And if you have an expression, you have a tree, and the evaluation of this expression is what we call an evaluation tree. And this evaluation tree will correspond to parse tree. And so we will use parsing to recover the possible evaluation tree corresponding to the template. And after that, we will filter them using abstract interpretation. So for instance, I have another output text here, which is the same as before, but I added some constant text after that.
Yeah, so I have this template, and I will over-approximate it using a context-free grammar. So the entry point of this grammar is the text, and then I've replaced the if instruction by a new node, and this node is either a constant text or int, which correspond to each branch of the if, and int is well, just a regular expression corresponding to what is an integer. And so, using that, we will have two parse tree. We will use ambiguous parsing. So ambiguous parsing does not report a single parse tree. It reports all the parse trees corresponding to all the possible parse trees of the program. And after that, the idea is to filter this parse tree using abstraction. So you know when you are doing a parser, you have these so-called semantic actions which corresponds to, basically they are a function which maps a parse tree to the text in the parse tree to some value. And this value here will be what I call abstract database, so abstractions of the possible database. So this is how it works. This is the first parse tree. Here, for constant text, I do not have any constraint. Here, I have a if, but I know that this if corresponds to the true branch, so I had to constrain that the condition C must be true. We propagate this. No constraint and C is true means that we have C is true. Here, the same, we don't have any constraints. Here, we have the constraint that X is equal to 3. When we combine them, just two different fields in the database. And in the end, this is a representation, as we say, a canonical representation of all the database that can output, of possible database that can output this text. Now we try with the other parse tree. For the other case, it was in the case when we output an integer. So now we have the constraint that X here must be 0. Here the condition now is that the condition is false, because it's another branch. Okay, we continue. Up to here, we have propagated this input. And here, we output X again, but this time with value 3. So when we try to unify the two constraints, we'll have X equals 0, X equals 3. And so it's not possible, so we return bottom. And this means that we will discard this parse tree as a possible parse tree that can output the data. So, what has this abstract database? Basically, they really mimic the concrete database, but we put sharp everywhere. Abstract database is an abstract scalar, an abstract record, and an abstract sequence. An abstract scalar is just a scalar, and a record is a map from a field to an abstract database. So all of this is very straightforward. The concretization is quite simple. And the only operation that we need to implement is abstract interpretation, abstract intersection, which corresponds to unification of the two constraints. And what is very interesting is that for the operation that we have implemented, all the operations are forward complete. And forward completeness is not a notion which is often used, but it's useful here. And we don't have joins or widening because we manage to be such that we don't need to compute any fixed point. The only complicated operation is the handling of sequences. So why are sequences hard? So a first problem, and I will not dig too much into it, but the idea is that it makes the evaluation of parse tree, you can have an infinite number of parse tree if you do it using the standard evaluation rules. So in this example, I have an iteration on a loop, but I have some if inside, and with the else that does not output anything. So we have some sequence of elements that do not output any value, which means that the length of the list can be infinite. And if we do it naively, we will have one parse tree for each possible size of the list, and it will mean that we have an infinite number of parse trees. So the idea here is to modify the collecting semantics so that we only focus on the elements that produce output and we remove the other one. And it's interesting because it's so fun in abstract interpretation that we have to work on the concrete semantics to help the analysis. And this is once again an example where we have to do that. Second difficulty is how can we relate elements? So here I have two iterations on the same list. One where we have some condition C and we print F. One where we use some condition D to know if we need to print G. And so we have this as the output. In the first iteration, we print 4 elements. In the second, we have 2. And the problem here is that we don't know how to match the different elements in the sequence. It may be that 1 here corresponds to 12, that 3 corresponds to 27, but it may be also that 12 corresponds to an element that was not printed in the first iteration. Basically, we don't know, and so this is a big source of imprecision, is that we don't know how to relate both elements. But there are some cases where we can relate elements, in particular, if we output a complete sequence. So now, what I do in this template is I print every element, the field F and field G of every element. So despite the fact that I do 2 iterations, then because I have outputted the complete sequence, we know that the sequence has 4 elements, and we can match by position, saying this one will correspond to 11, this 3 to 33, etc. And why we can do that is because we have outputted the complete sequence. So it may seem a bit ad hoc, but actually it's completely semantically justified, and it's very important in practice to have this kind of rule to recover the loss of precision. There are other possibilities. For instance, if we know that some fields like F are output twice in both sequences and they have a unique value, then we can use them to match the contents of the other fields. So there are other things that could be implemented. And again, this showcases one of the benefits of abstract interpretation is that it's really easy to add new domains to improve precision and to do that in a principled and compositional way. So we performed an evaluation. So the motivation of this work was an industrial contract, and we were given a collection of industrial template files and to see if we could do something about them. And because it was it was a custom language designed by industrial people, which were not programming language specialists, which means there was a lot of syntactic sugar and a lot of various constructs that basically could be regrouped into somewhere if you desugar them. So basically a lot of the work was to take this language, take a core calculus of this language, and desugar the complex language into the core calculus. And we also had some interesting extensions that are present in the paper where we can handle truly recursive calls, etc. And this is one case where widening will be useful. So you can refer to the paper for these extensions. And we implemented manually a backtracking ambiguous parser. So initially, we used a parser generator. It was DeepGen, and it was very awful in performance. And whereas the manual backtracking version works very efficiently. And one of the reasons why backtracking works so well in this case is because in templates, you have a lot of constant text. So often when you backtrack immediately. You don't have to analyze a lot of text before realizing that you need to backtrack. So actually, it's almost linear. And we can see that for files that are not completely trivial, we analyze, we cannot even measure the time needed to perform the analysis. And in all the cases that were given to us, we were able to analyze them fully precisely, meaning that it corresponds to the fact that in the end, we have the value of all the paths in the database that were mentioned in the template. And of course, for the other one, we don't know. And we have some theorems that relates forward completeness to this notion of precision. So in the end, it means that it was possible to recover the database in each case, and we didn't even need to modify the templates. We were prepared to do that. We are in a favorable case where basically we can ask to the user to modify the template in order to help the analysis. Often you have some analysis where you can do that, and it's often much harder than when the code is made to be analyzable. But in practice, we didn't need it. So for instance, it would be possible to add some
custom code to transform incomplete sequence into complete sequence, things like that. If the solution arises in the future, but if the problem arises in the future, but it was not needed. So to conclude, what we really did was just applying the standard abstract interpretation method to solve a new problem. So what is this method? It's just formalize a concrete and a collecting semantics in a way that will suit your analysis. In this case, the collecting semantics is a reverse evaluation, and the fact that we handle a set comes from the fact that the analysis is not, the evaluation is not injective. Then we have adapted the semantics to the need. Here we needed to have a finite number of evaluation trees to handle the termination, and also the way that we handle sequence make it so that we avoid the need of a fixed point computation, which could have lead to a loss of precision. Then we need to design the abstraction and its relation to the collecting semantics, and the analysis follows automatically. So here we designed abstract domains for precise constraint propagation, and the only operation that we need was the intersection. So actually we also use the power set completion domain to handle the different parse tree inside the analyzer. We didn't need a join or waiting. And finally, we use the concept of abstract interpretation to understand and to improve the analysis. And notably, we use the concept of exactness or forward completeness or gamma completeness to understand where we lose precision in the analysis. And in the end, with a combination of suite-up domain and with some template writing guidelines, in the case where we are not fully precise, we were able to completely solve the problem. So yeah, in the end, abstract interpretation could address all the limitations of existing methods, such as non-termination, existing injective program only, and absence of composition of abstraction. So I think this really showcases the benefits of using abstract interpretation. Thank you.
Right, thanks for the talk. Do we have any questions? I'll start us off then. I'm interested in the use case of generating parsers out of pretty printers. Do you have an intuition of how that would compare to like traditionally written parsers, both performance-wise, or is there a class of languages where you wouldn't sort of say top or where you wouldn't say bottom in using your method?
I think in our case it worked quite well because, as I said, when you have templates, you have a lot of constant fixed text, so backtracking works well. But I think we could have used some better parsing algorithms, and nowadays you have the GLL parsing algorithm, which works quite well, so I could have been using that instead. Yeah, basically we convert the pretty printer into an ambiguous parser, and then we remove the spurious cases. And so it depends on the performance of the ambiguous parser. But now I know that GLL, for instance, works well. So in theory, it should work well.
Oh, sorry, then I may have misunderstood the use case, but I thought you could also take this technique and then for a language for which somebody only wrote a pretty printer, you perform your analysis, and then that essentially produces an AST of the thing that was previously just pretty printed, right?
I'm not sure I understood fully the question.
Maybe we'll take it offline instead.
Okay.
Let's see if there's any questions here. If not, I have another one. Do you think an SMT solver would be helpful for the sequence matching problem like that, where if the SMT solver said unsat, you could automatically see that there is no way to match up the elements, and if it gives you a model, you could try to use that?
Yeah, so we did it using abstract interpretation, and so the complexity of the analysis is very, very efficient. Somehow, I think we could have instead computed a formula over sequences and using SMT solver to solve this sequence. Problem is that I'm not sure how decidable are these SMT theories over sequences. And also probably the time will have been less deterministic. But probably this could be tested. And in other case, because we use abstract interpretation, we could integrate this technique with this one and use it whenever it is necessary.
Yeah, it could be one of these, could be just another domain you sort of intersect with when you run into the sequence case.
Yeah, exactly. Yeah,
that sounds
yeah.
reasonable. All right, any other questions? Let me check online as well. No questions online, so in that case, let's thank the speaker again.
Thank you.
All right, and our next speaker is Shangtong Cao, who's going to be remote and will tell us about WebAssembly. Let's see if that works. Can you hear us?
Yes, I can.
All right, great.
Can you see my slides?
Not yet.
Position to this window. Yeah, everybody can see you now.
Okay, okay.
Just watch the stream. So you may start presenting. I believe everybody can see, right?
Yeah, we can see you now.
Okay, okay. Hi everyone. My name is Shangtong Cao. Today I will take a presentation of our work, BlueWasm, a general static binary writing framework for WebAssembly. First, I will take a talk about our work's motivation. Let's take a quick look at WebAssembly. WebAssembly is an emerging stack-based bytecode, aiming to execute at native speed. WebAssembly is originally to be applied in browsers as a complement to JavaScript for its fast execution. The portability of WebAssembly is achieved by the ability of being a companion target of popular programming languages, such as C++, Rust, and Go. And the WebAssembly binary is executed in the sandbox environment of browsers or runtimes. The development trend of WebAssembly is very promising. So it is supported by more than 19 browsers, and it also has more than 10 non-web runtimes, which are specifically developed for it. WebAssembly is widely used, both inside and outside the browser. So we can see it can be used in game engines, scientific computation, and video decoding. And due to its portability and safety, WebAssembly has been extended beyond the browser, such as serverless, edge computing, and blockchain. Although WebAssembly has many application scenarios, it has no dedicated rewriting framework. And a lot of WebAssembly's current work involves binary writing. So we think a general proposed writing framework is necessary to facilitate the research on WebAssembly binaries. Since the most of what I'm going to talk about is binary writing, let's get to know the binary format of WebAssembly. First, like other binary formats, WebAssembly has magic number and version number for identification. And each WebAssembly binary is composed of sections with different functionalities. Something special is that there are two kinds of sections. The one is a single section, which can function on its own. The other one is a complementary section, which works together with another section. Let's look at a simple section first. The type section contains all the function signatures in the binary, and the start section indicates the entry function of a binary. All global variables are declared in global section. The content in custom section are unrelated to the execution. Most of them are debug information. The import and export sections declare the import and external item, such as the function, variable, and memory. The function and code sections declare all the internal functions. And the indirect functions are declared in table and element section. Lastly, the memory and data sections declare and contain the initial memory data. Implementing a general purpose binary writing framework has 3 challenges. First, conducting efficient and effective static binary writer is strongly related to the complexity of the written binary. As we talked about before, WebAssembly binary has 11 valid sections to be written. We need to design the writing functions for each section. The right finger demonstrates a WebAssembly binary in text format. Let's look at the simplest type section. In the second to first lines, we can see 2 types. They belong to type section, and each type is a vector. It has several attributes, the params and the results. This situation is similar for the other sections. So each section in WebAssembly binary is composed of vectors. Each vector has several attributes. From line 8 to line 14, each vector, we can see the instructions of the main function. They are structured and the relationships between instructions are nested. Therefore, the syntactic complexity of WebAssembly makes it challenging to implement a general writing framework. The second challenge is that WebAssembly has a strictly static verification before execution. For example, sections are composed of vectors, each of which is indexed by an index. Let's take a look at the function and the type section. The elements in type function section are a list of indexes. They point to the function signatures in type section. If we insert a new type at index 1 in the type section, but don't update the function section, it will make the original syntax and semantics error, because the function signature of the function with index 1 is changed. Similarly, all functions with the signature index greater than 1 will be changed. So if a user inserts or deletes a vector, he has to update the vectors of the whole sections to ensure the continuity of indices. Any negligence will invalidate the written WebAssembly binary. The last challenge is that the sections in WebAssembly binary are functionally coupled. Some functionalities should be achieved by combining multiple sections. Let's take a look at the process of invoking a function in WebAssembly binary. There is an internal function named add and indexed by 2 in this example. First, its readable name is contained in the custom section. 2 often is a signature. We need a 2-layer translation through the function section and the type section. Its implementation, the local variable and function body can be accessed only in the code section. It's worth noting that all imported functions are located in front of normal functions. So we need to subtract the number of imported functions, which is 1 in this example. Such a section coupling raises another challenge for the users to achieve his high-level functionalities. Thus, how to address these challenges are mainly focused by our framework. We designed and implemented Brovasam, whose architecture and workflow are shown in red. As we can see, Brovasam is composed of 4 components: Wasm parser, section rewriter, semantics rewriter, and Wasm encoder. Based on Brovasam, we can implement many applications, such as binary truncation, obfuscation, auto patch generation, and mutation. Let's see how the Wasm parser and Wasm encoder work. As we mentioned before, WebAssembly has a highly structured and complicated format. In order to enhance readability and facilitate the rewriting process, we had unnecessary and verbose details and translate WebAssembly binaries in a semantical equivalent format. We refer to the official WebAssembly specification and formally define the relationships among sections, elements, and fields as shown in red. As we can see, each section is composed of a list of elements with the same name, where elements are composed of several fields. Wasm parser and encoder convert the WebAssembly binary and the formally defined objects to each other. For each section, we have defined a class with its fields as attributes. Each element is an object of the corresponding class. As we can see, the Wasm parser will pass the left binary to the right objects. Through the opposite direction, the Wasm encoder can translate and resemble these objects into a WebAssembly binary in a lossless way. The Wasm parser and encoder provide the basic of a rewriting framework. Let's see how section rewriter interacts with these objects. First, the section rewriter plays a vital role for Brovasam. It provides 4 basic APIs that allow users to manipulate sections on fine-grained level. They are select, insert, delete, and update operations. The select operation takes an element template to filter out elements. And based on the selected results, the insert and delete operations can be conducted to insert a new element in the specified location and delete the given elements. The last update operation can be used to modify a field by a new value. I will illustrate an example of using section rewriter. First, if I want to delete the first type in left objects, before I invoke the delete operation, I need to specify the element to be deleted. So I make the result of select operation which represents the first type as parent. And then I want to insert a new type at the end of the type section. In addition to using a select operation to specify where to insert, I should prepare the new type element, noting that the wildcard under 3 character is allowed when designating a field. The semantics rewriter is implemented on section rewriter. Developers implementing rewriting functions generally go through 3 steps. They first need to understand the binary format of WebAssembly, and then they will using a series of section rewriter APIs. But they have to solve the section coupling problem which we have mentioned before in the end. This process is also important for those who have some knowledge of the binary format but need to quickly implement their rewriting functionalities. To ease the burden on users and improve the usability, Brovasam provides a semantics rewriter. We have conducted a comprehensive survey in real-world scenarios on applications that require binary writing. And we abstracted 5 semantics shown red, which cover all 11 sections and offer 31 APIs in total that can be used by these applications. Let's say a simple API provided by semantics writer. The append internal function API as a function at the end of all internal functions. And it will modify the type and function section depending on the first 2 params. The last params will be used to modify code section. Therefore, if developers use this API to add a function for a WebAssembly binary, they will skip many steps compared with using section writer. The semantics writer greatly accelerates their development speed. Let's review the whole writing process of BWASM. First, the WASM parser takes a WebAssembly binary as input and parses it as a list of objects. And then the section writer and the semantics writer provide many writing APIs for developer to manipulate the formally defined objects. After all the writing APIs are processed, the WASM encoder will encode the earlier objects to WebAssembly binary. Our evaluation is driven by the following 3 research questions. First, is it efficient to conduct WebAssembly binaries writing through APIs exposed by BWASM? And whether the APIs provided by BWASM are implemented correctly and effectively. Finally, can BWASM be easily applied to real-world scenarios? We need some representative WebAssembly binaries to evaluate the BWASM. Due to some API require many effort to determine the params by the content of binary, we will select 10 WebAssembly binaries from WASM Bench, a well-known micro benchmark that collects tens of thousands of WebAssembly binaries. We can see that they are compiled from various programming languages and cover 2 typical applications of WebAssembly. Moreover, they range in size from 3 kilobytes to 4 megabytes, which will evaluate the ability of BWASM to handle WebAssembly binaries with different sizes. The semantics writer exposes a total of 31 APIs, which cover all the legal sections of WebAssembly. Therefore, an evaluation on their efficiency is essential to evaluate BWASM's usability. We invoke each of 31 APIs with proper arguments 1,000 times and record the consumed time. Part of the time results are shown here. Generally, the consumed time of writing are related to the size of WebAssembly binary. It is worth noting that in this experiment, each API call requires a parsing process and an encoding process. On average, it takes around 1.3 seconds and 0.5 seconds to parse and encode a WebAssembly binary. And as a one-shot overhead that the parsing and encoding time are acceptable. Moreover, we can easily observe that each API takes only milliseconds or even less than a millisecond. Interestingly, among all these APIs, the operations related to insertion consume more time than other type of operations. This is because inserting an entry into a section requires fixing indices of subsequent entries to ensure continuity between indices. correctly and efficiently achieving the corresponding goals through APIs plays a vital role for Brovasam. To evaluate the effectiveness of semantics rewriter, we pass all rewritten binaries in RQ1 to official syntax validator, the Wasam validate, to check the correctness of the syntax. And we manually double check all binaries to make sure the results are in line with the original intent. Based on the results of the verification tool and manual checks, we can conclude that this semantics API perform correctly in both syntax and functionalities. Lastly, we demonstrate the practicability of Brovasam by illustrating some real scenarios that require writing WebAssembly binaries. The first one is binary instrumentation. Wasabi is a dynamic analysis framework built on instrumentation of WebAssembly. It specifies instrumentation rules for instructions to obtain runtime information during execution. There is the instrumentation strategy for the call instruction. We can say Wasabi appends two imported functions named callPre and callPost in this binary. Then Wasabi invokes them before and after the original call instruction to record params and returns of the fifth function. Let's take a look at how easy it is for Brovasam to implement the equivalent functionality. As we can see, it only takes 16 lines of code to implement it using Brovasam. If developers use Brovasam, they can make a little effort to implement the instrumentation strategies of Wasabi. Besides, due to the fixed pattern of instrumentation used in Wasabi, modifying the underlying code is unavoidable to achieve other specific binary instrumentation. In contrast, Brovasam provides a large number of instruction-related general writing APIs, making it more flexible and convenient to implement the required instrumentation functionalities. Brovasam also can be used to implement software hardening. Even though WebAssembly runs in sandbox environment, certain types of bugs may still be exploitable within the WebAssembly binary. For example, there is no protection mechanism for the stack memory of WebAssembly. So the traditional attack, the Stack Overflow, can exploit WebAssembly binaries leading to out-of-bound read and write. However, through Brovasam, developers can easily conduct software hardening. Let's take a look at this example. The callee function is originally potential for buffer flow. After the hardening, it is wrapped by the hook function, which inserts a stack canary and validates its integrity around the invocation to callee function. An implementation using Brovasam is shown here. As we can see, the most of code are related to the design of canary insertion and validation. The convenience of this implementation is attributed to the semantics rewriter APIs. They offer many practical functionalities. Lastly, Brovasam is applicable for fuzz testing Wasam runtime. One of the widely adopted fuzzing approaches is to mutate the existing files and fed them to runtimes. The Wasam mutator is a tool for fuzzing Wasam compilers and runtimes. Wasm mutator can mutate the given WebAssembly binary while keeping semantics equivalence. One of its mutation strategy is binary structure mutation. For example, introducing a function to the binary. Let's see how easily Wasm can implement it. Implementing adding function mutation in Wasm mutator requires more than 100 lines of code, while it only needs 18 lines by using Wasm. This is because there is no rewriting component in Wasm mutate. Thus, it has to decode and encode the relevant sections. In contrast, Wasm passes the entire WebAssembly binary into objects, which simplifies many extra operations. Additionally, since Wasm implements the semantics rewriter, inserting a function only requires invoke a single section or a single API. Let me conclude. We have implemented Wasm, the first general purpose WebAssembly binary writing framework, and the open source address it here. We perform extensive evaluation on diverse WebAssembly applications to show the efficiency and correctness of Wasm. Finally, we show that it is useful, effortless, scalable, and user-friendly to implement a diverse set of binary writing tasks based on Wasm. At last, I appreciate each and every one of you for taking the time to listen to my presentation.
Shangtong, can you still hear us?
Yes, I can.
Sorry, what's that? Can you still hear us?
Yes, I can hear you.
All right, great. Yep, yeah, you can. All right, I got one question. So you mentioned that the WASM binaries get validated before they get run. While developing WASM, were there any checks that the validation does that were particularly hard to get right after rewriting when you were reassembling the binary?
I'm so sorry. My English listening is not very good. Could you please speak more slowly?
Sure. Were there any validation steps that this WASM validate performs that were complicated to make them correct in WASM?
Yes, the WASM will not check the syntax and the semantics correctness when the writing APIs were invoked.
Yep, makes sense. Do we have any questions in the room? Last chance. Nope. In that case, let's thank the speaker again.
Oh, you're welcome.
And the next session starts at 4. So we'll see you then.
Okay, come in. So welcome to the quantum session, the last one of the day. And please come in, okay? First speaker is Yan Bin Chen, is a joint work with Yannick Stade, quantum constant propagation.
Yep.
Okay?
Yep.
Please go.
Yep. Thanks for introducing. And I'm happy to be here to present our work, quantum constant propagation. Quantum constant propagation, sorry. I think it would be very useful for you to give you a bit of background knowledge if you have not heard of what a quantum computing is. So let's start with the notations, very common notations which we will use in quantum computing. So in quantum computing, we often use CAD notations to denote column vectors. To give you an example, if you think of a space of complex vector of length 2, then actually we have two computational basis vectors denoted respectively by ket0 and ket1. In this sense, any complex vector of length 2 can be expressed by a linear combination of ket0 and ket1. We could also go to a higher dimension. Say we go to a dimension of 4. Then here we have 4 computational basis vectors, namely ket0, ket1, and ket2, ket3. However, here we use, as you can see, binary representation for 0, 1, 2, 3, which is also very common. Another common operation, which is tensor product or Kronecker product, which is defined to be, if we have two vectors, v and w, then the Kronecker product, v tensor w, is defined to be, we first just write out the vector v, each entry of v as it is, and then we attach vector w to each entry, and then we expand out the vector w. So in the end, we get a vector of dimension, which is a product of the two input vectors, a product of the dimensions of the two input vectors. Now, let's talk about quantum computing. So we all know about classical computing. So say if we have a classical computer with m bits, we know that we can use a binary value to represent the state of a single bit. So we can stack all these m bits together, and then we have a column vector of length m. So we use this to represent the state of classical computing. Then we have a circuit, which is a low-level representation of algorithms. The circuit acts upon the state, and then we get an output state, which is again a column vector of length m. However, things become different in quantum computing. Say if we have a quantum computer with n qubits, where a qubit is a quantum counterpart of a bit in the classical computing. To denote the state of a single qubit, we can only use a vector of length 2, a complex vector of size 2. And the initial state of the quantum computer is denoted by the tensor product of all the initial state. So as you recall from the definition of the Kronecker product or tensor product, you will eventually get a vector of length 2 to the power of m. Then we have a circuit. We have a circuit, quantum circuit, which is also a low-level representation of quantum algorithm. This circuit acts upon this initial state, and we get an output state, which is again a vector of length 2 to the power of n. However, if you are careful enough, you will see that here I didn't explicitly express the output state in terms of each of the qubit states. This is because if you apply quantum gate, then qubits get entangled with each other. So in general, there is no way to separate qubits from each other. So there is no way, generally, to express the state in terms of individual qubits. So you can see from here how challenging it is to simulate a quantum computer in a classical computer, because even denoting the state of a quantum computer needs an exponentially number of costs, let alone performing a computation upon it. Let us back to our point. Why do we propose our optimization? Currently, quantum gates are very expensive and yet very noisy. That is, if you perform a quantum gate, there is a chance that you introduce a noise into your state. So to counteract this fact, the straightforward idea is to say, okay, we just wish our circuit to contain as less number of gates as possible. And we also wish the gates in the circuit to be as simple as possible. Generally, a gate is considered to be simpler if it acts upon less number of qubits. We will see what it means very soon. And we will perform, since this optimization is performed on a classical computer, we wish this optimization to be as efficient as possible. So in this sense, we kind of push some of work from the quantum computing to the classical computing, because the classical computing is a world which we are all familiar with, and we have many sophisticated methods, and there is no error if we perform a classical gate. Now the idea is that we can propagate initial configuration throughout the circuit, and then we take the information we propagate to simplify the circuit along the way. This is kind of similar or analogous to what we do in static analysis. If we try to simplify a function, and we know that the input to this function is limited to a certain range or domain, then we know, okay, maybe this block of the function can be eliminated given this input. Let me give you a very toy example. So if we have initial configuration of all ket0 state, and we propagate this information to the point indicated by this dashed line here, then you can see that the middle gate, this gate, is actually redundant. Why? Because the information here tells us that the first 2 qubits, the top 2 qubits, is either 0, 1 or 1, 0. So one of the qubit is disabling the gate. So this gate will never be applied. So we can remove this gate entirely. After we have done so, you can see we can pairwise remove these 2 C0 gates, a C0 gate, these 2 X gates, these 2 C0, and these 2 hard mod gates, because those gates are both unitary and Hermitian. Then in the end, we will get a trivial transformation upon the quantum system. Even if I told you that this example is a very toy example, this optimization here I show you is not yet adopted by standard optimizer of the quantum of the existing sophisticated quantum circuit optimizer. So this also strengthens our contribution in this work. So how can we do this? So because as I have told you, it's exponentially hard to simulate the circuit. So actually, if you really wish to propagate the initial configuration throughout the circuit, it is also the equivalent to simulating the circuit classically. So how can we achieve this? Let's look at some existing approaches. One approach, the relaxed peephole optimization. So they have an idea. So they say, okay, we only track the state of each single qubit. So that is, they only track pure state. In this sense, they use an automaton where each node in it, it is disappearing. Why? Let me reconnect it again. Okay. Yeah. So where are we? So this RPO approach tracks only pure state, and like each node denotes some state of the qubit to be tracked, and it goes from one state to another if you apply a single qubit gate upon it. However, there is a drawback that once you apply a multi-qubit gate onto this system, you lose all the information. So as you can see, you will go from ket 0, you will go to the state of top, meaning you know nothing about this qubit because it gets entangled with the rest of the system and lose its purity. Another approach, EXO. So they say, okay, maybe at this point, so we simulate the circuit to some point, and then we just send this circuit up to this point to be executed onto the quantum computer for many shots so that I can get the probability distribution characterized by the state described here at this point. And I set a threshold, and I kind of drop all the peaks which is below the threshold so that in the end I can get another probability distribution which could likely, or could hopefully be approximating the original distribution, but the information density you need to represent the state is significantly lower. However, there are two drawbacks for this method. The one is that you need a quantum computer to perform this optimization. Another drawback is that you are leaving out some peaks. So kind of there is a risk of inaccuracy as you go on the simulation of your circuit. So our approach tries to counteract these drawbacks. Our approach can be performed entirely on classical computer. It can run efficiently, and it will not give up when some entanglement is formed. How do we do this? Basically, we kind of design and implement the data structure like this. So we have a table where each entry corresponds to each qubit, and initially each qubit is inside its own entanglement. If during the execution of the circuit, qubits get entangled, we put these entangled qubits into the same union. And inside each union, we maintain only non-zero coefficients of the computational basis. In this sense, for this example, instead of using a vector, a complex vector of length 32, we only use 1, 2, 3, 4, 5 pieces of value to represent the state of our system. However, we also need to guarantee that our optimization can run very efficiently. So here we set a number, a max. So this is a threshold which we say, okay, if one entanglement gets just too complex, so that the number of non-zero coefficients in this entanglement is exceeding a max, then we set this entanglement to top, so that we give up upon only this entanglement, but we still have track upon the rest of the system. So by doing so, we can guarantee our optimization to run fast. Now, let's talk about how are we going to use the information we are propagating to simplify the circuit. Let's consider a few words on what a control gate is. So say a control gate is a gate like this. It has a control wire and a data wires. So if a control wire receives signal 0, then the gate is disabling, then this gate is not applied. If the control wire receives 1, then the gate is applied. Let's have a look how are we going to use the information we propagate to simplify our circuit. The first simple case is for a control gate to receive always gate 0. At 0 gates, then we know that this gate is always not applied, so we just remove the entire thing. In case we know that this wire, the input is receiving always 1 because 0 and negates of 0 is 1, then we know that this gate is always applied, so we can remove this control signal because we don't need it. We know already in advance that this gate is always going to be applied. So here, by doing so, we kind of simplify the complexity of the gate. Let's talk about a more complex case. So look at the state here, indicated by the dashed line. If you look at the first control, then you will find actually this control could be either 0 or 1, because it gets 0, 0, 1, 1. So actually the first case cannot be applied. And the second case can also not be applied because it is not always 1, it could also be 0. And the same reasoning applies to the second qubit. It could be either 0 or 1. But in this case, we could still do something about this gate. So if you look carefully enough, then you will find actually the information given by the first 2 qubits is implied by the third qubit. Because if the first 2 qubits are enabling the gate, then so is the third qubit. For example, if the first 2 are already 1, then the third one is always 1. If one of the first 2 qubits are disabling the gate, then so is the third qubit. So you can see if one of the qubits is 0, then the third qubit is also 0. So in this sense, we know that the first 2 controls are redundant, so we can already remove it. So this is the high-level idea of our implementation. We have implemented our quantum constant propagation as an artifact, and we wish to evaluate how it works. So we evaluate our optimization method on this Munich quantum toolkit bench. This is developed by one of the groups in Technical University of Munich. It has 28 algorithms, scalable in number of qubits, and in total 1,761 circuits. Because it is very normal for modern compilers to have multiple optimization passes and compose those passes together to get a better effect. So we wish to test how much more the overall optimization can achieve by composing in our optimization. So we consider 2 existing optimizers, PISC, Qiskit, and TCAT, and we we wish to measure how many more gate count reduction and control reduction we can achieve by composing in our optimization path. And as you can see, in terms of gate count reduction and control reduction, by composing in our optimization path, these 3 existing optimizers can benefit very much. We wish also to compare our optimization with the RPO method. Recall that this RPO method is also taking the idea of information propagation, but it only tracks the state of pure state. It only tracks pure state, namely single qubit. And as you can see, either composing our path before or after RPO, the overall optimization can be facilitated. Actually, if you set the Nmax, that is the allowance for the entanglement complexity, to be 1 or 2, then our optimization can only track single qubit system, which is completely subsumed by RPO, which this fact is also demonstrated if you look at here, at this column 1 and 2, at this column 1 and 2. So this is like, by composing, so if you set the Nmax to be only 1 and 2, then by composing in our optimization path, the overall case is deteriorating. But however, if you allow for a larger Nmax, then actually the overall effect can be significantly improved. So this also showcases that our method is not subsumed, and it offers much more than already existing. We also wish to show that our optimization can run very efficiently. Here, to test these, we kind of choose the circuits for quantum Fourier transform with qubit number 2 to 129. The reason for that is this set of circuits grows quadratic. So the circuit in this set grows, the number of gates grows quadratically to the number of input qubits. And it also produces a very complex entanglement amongst qubits. So in this sense, if you try to simulate the circuit naively, these set of circuits guarantee to reach you a very complex and challenging case very soon. And looking at this plot of our runtime, you'll see that actually, looking at this trend, our runtime only grows polynomially to the number of input qubits. And as you increase the allowance for the complexity of the entanglement, the time required to complete the optimization will be increased. However, you can see that even for the largest number of Nmax and for the most complex circuit, our optimization can terminate, can complete its work within an acceptable amount of time. So as a summary, our optimization tries to reduce the circuit's complexity by removing superfluous controls and controlled gates. It does so by performing a restricted but computationally efficient simulation upon the circuit. The key feature of our method is that we kind of maintain a data structure which kind of separate entanglement groups in separate data blocks. But we also have to admit that our method is limited by the number of, by the value of Nmax, which is our allowance for the complexity of the entanglement. So if the circuit, one entanglement gets more complex, then our method will give up upon the entanglement. Okay, so thanks for your attention, and
thank you.
Yeah.
Thank you. Questions? Come on. Be entangled with the speaker.
So, thank you so much for your talk. So I would like to ask you, does your method have a way to recover from the situation where you have top, let's say, because I expect like the more you go further in the circuit, the more qubits will become entangled, and so at a certain point, maybe everything is top. And can you recover from this situation? Thank you.
So actually, there is existing method that can recover from the top. Let me show you. So if you look closely at the state, the automaton here, and you see you can go from top to some certain state, but this is achieved by programmers making some annotations inside the circuit. So if, so if the programmer are sure about at some point the state of the circuit, then you can indeed recover some information, but this is not accounted for by our optimization because we kind of wish to rule out the influence of the programmers.
Okay, other questions? I have one, maybe. In the last slide, you mentioned limitations, and in the slide before, in the 12, if you go to slide 12. 12.
Yeah.
Yeah, the shape in that corner on the right bottom corner is completely different. Is that because of the limitation and the entanglement grows?
Oh, you mean the one for 4,090?
Yeah, that one, yeah.
Yeah, I would say it's still in, so because I think it's those outliers, so we kind of have to scale the graphics in a way that also includes these two.
Ah, okay.
So,
no, that's the right.
But the shapes are similar.
Okay. Okay, so let's thank the speaker. Oh, there's some time for another question.
So maybe a bit of a naive question, but like the way I imagine when you're doing quantum computations is that you get a lot of the advantage from these entanglements. So do you have maybe some kind of intuitive reason, because your approach, it still seems to manage this and it still seems to work. So do you have some intuitive reason to explain why kind of the states, even though they do entanglement, they don't get so crazy complicated that you can still handle it with your technique?
So just to repeat what you're asking, to make sure that I understand what you're asking, are you asking like if the circuit gets too, so the entanglement in the circuit gets too crazy, then is there any guarantee that my method can still handle it?
So I think the question, I guess, is more that like, how is it possible that kind of these algorithms that you took a look at don't get so crazy that the method does still manage to handle it? And kind of what's the intuition, or how, yeah, why do the algorithms not get so crazy entangled just a little bit?
Well, I think, so if the circuit gets crazily entangled, so the qubits in the circuit gets crazily entangled, then this is the situation where our optimization wish not to touch upon. Let me give you one justification why. So if you look at this method here, so this Axel method, they kind of, what they try to achieve is quite similar to what our purpose is, but they kind of drop out these low peaks at here. So in case where the qubits are crazily entangled, then the cases are which those peaks are so on average very small. So there could be a case where the threshold is, it could be above all these peaks. So then you kind of drop out all the distributions that you have, then you lose anything. So kind of, it's even bad than top, because it's like you're losing all the valuable information on the system. So as you said, the quantum algorithm kind of benefit from those complex entanglement. So if the entanglement is truly entangled, is truly complex, and then we can kind of wish to keep it. So does it answer your concern?
Yeah. I mean, I can ask offline.
Yeah, sure.
Okay, I think it's okay. So let's send the speaker again. Next speaker. Okay, so next speaker is Xuezhou Tang, Xuezhou Tang, and joint work with Ye Zheng, and boosting multineural convex relaxation for neural network verification.
Yeah. So let's begin. Good days, ladies and gentlemen. I'm Xuezhou Tang from Shenzhen University, and I'm also the authors of the Boosting Multineural Convex Relaxation for Neural Network Verification. And the other two authors are Ye Zheng and Jiaxiang Liu. Both of them come from Shenzhen University. In our practical life, because of the weak interpretability of the deep neural networks, also called as the DNNs, its inputs are always be easily perturbated by some perturbation in nature or the human beings. And such perturbation cannot be detected easily by human beings. And then the perturbated input will be sent to the DNN and get the wrong result with some wrong classified result. For example, there is a picture whose original label is an owl. It's an owl, and it will be perturbated by the perturbation delta. Then for human, it's also an owl, but for the deep neural networks, its output may bring the incorrected result as the grass label. For example, grass or others except for the owl. In this situation, we consider that the DNNs is not safe for the original input under this perturbation. But the current testing technicals cannot guarantee the safety for the DNNs, so the verification for DNNs is proposed. It aims to answer the question whether the output of the DNN will satisfy some properties under the perturbation delta. For this example, the property is that the output of the DNN is the same as the original label of the input. Here's the perturbation domain of the input, which is consisted of the perturbated input, and we marked it as theta. The theta is a kind of p number whose radial is delta, and it is a convex domain. For testing technologies, they just select some samples from this perturbation domain and test their corresponding outputs, so they cannot guarantee the safety for DNNs. Compared with it, the verification for DNNs try to verify any perturbated inputs from the perturbation domain and answer the question about whether the output of the DNN will satisfy the properties. And if the property is satisfied for all the perturbated inputs, the DNN is regarded as being safe for this input under the certain perturbation. Firstly, let us describe the process of DNN briefly. For the one layer in DNN, there is an input vector which will be multiplied by the wet vector. And the multiplied result will be added to the buyer's value. The result is called as the activation input, which will be inputted into the activation functions, maybe ReLU function or sigmoid or any other functions you like. Then it will get the answers named as the activation output. The activation output will be the input for the next layer. For example, there is an input vector x consisted of x1, x2, and x3, which is three-dimensional. Then it is multiplied by the three-dimensional weight vector w1 consisted of w11, 12, and 13, marked as the red line in slide. Then it is added to the buyer's value b1, then get the activation input z hat 1. The z hat 1 will be calculated through the activation function and get the activation output z1. Then the z1 will be the next input for the next layer. To answer the question whether the outputs will satisfy some perturbations, we should discuss the relation between the input and output for the DNN. But it is hard for us to describe such relation because it is non-linear relation. It is hard for us to discuss. So, to discuss such relation, the single neural relaxations are proposed. It can transfer the non-linear activation, non-linear relation between the input and output to a linear one. The non-linear relation meaning caused by the non-linear activation functions like ReLU or sigmoid. In the slide, the red line marked is the ReLU function. The single neural relaxations methods use some linear constraints over approximated the non-linear activation functions to transfer the relation from non-linear to the linear. Such as for ReLU functions, some methods use the following grid shapes to transfer the relation. The grid shapes, we can see that are consisted of some linear constraints or linear relaxations. So we constrain the non-linear activation function to some linear constraints, and maybe we can use SMT solver or LP solver. LP solver is a linear program solver. The non-linear relation is transferred to be the linear one. We can notice that the single neural relaxations are discussing the relaxations between the activation input x1 and the activation input output y1 of just a single activation neural. For example, y1 just to x1 and xn just to yn and so on. In other words, y1 is constrained by the relaxations only between x1 and y1. That is proved that the single neural relaxations may face some convex relaxation barrier which limits its precision. To overcome this barrier, the multineural relaxations are proposed. The multineural relaxations discuss the activation inputs and the activation outputs among k neurals. The k means the relaxations discussed among k neurals, and k is not less than 2. The multineural relaxations methods will generate some 2k dimensional relaxations based on the groups of k neurals. For example, when k equals to 2, the multineural relaxations will generate a 4-dimensional multineural relaxations R, X1, X2, Y1, and Y2 based on the group X1 and X2. So Y1 and Y2 are constrained by the relaxations, which is tighter than the one from the single neural relaxations. And the experiments shows that the multineural relaxations can overcome the barrier from the single one. It's ideal to compute the relaxations of all possible groups of k neurals, case mentioned before, but it is impractical because of the huge computations, which is 2k dimensional. So there are questions about which and how many groups should be selected for the generation of multineural relaxations. The state-of-the-art like K-poly and Prima use static strategy with hyperparameters empirically to select the groups. But such static strategy will make the multineural relaxations methods perform differently while facing different verification problems. For example, for DNNA, maybe the static strategy will make the methods perform just so-so, but for DNNB, maybe it will perform well. Here's the static selection strategy workflow. It will firstly divide the neurals in one layer into several parts, and then in each of the parts, it will generate the groups of k neurals. K is the relaxations discussed among k neurals. Then the selected groups are sent to the SPLM algorithms for their multineural relaxations. The SPLM algorithms is split bound and lift methods, which is used to generate the multineural relaxations. It will firstly generate the k-dimensional relaxations of activation inputs among k neurals. And then it will further generate the 2k dimensional generations, which is the final multineural relaxations. For example, when k equals to 2 and we assume that the neurals in one they are divided into two parts. They are VI to VI minus 1 to V1 and VI to VK. Then for parts V1 to VI minus 1 and VI to VK, the strategy will generate the groups of 2 and send them to the SPLM for the multineural relaxations. In other words, the V1 cannot be grouped with VI or VK, or we can see that any neural in groups in parts V1 to VI minus 1 cannot be grouped with any neural among VI to VK. That's a situation that maybe the group V1 and the VI may contribute a lot for the whole relaxations, but it is eliminated by the static selection strategy. So to overcome this problem, we propose a kind of dynamic selection strategy named Figma, based on the following observation. We observe that there may exist some relaxations from groups implied by the relaxations from other groups. And such relaxations are regarded as the redundant relaxations. For example, when we are computing the intersection of several sets of relaxations for the reachable set in the DNN, and the relaxations are C1, C2, and C3. We can see that the C1 are implied by the intersection of C2 and C3, and the intersection of C2 and C3 is marked as the red part in the slide. The C1 concludes the red part, so the C1 are implied by it. And C1 then are regarded as the redundant relaxations. Such redundant relaxations always have bigger volume in space, and the relaxations generated by SPLM are all convex, so we can compute its volume and select the groups based on these volumes. But it's also impractical for us to compute the volumes of relaxations from all possible groups of K, because it's equals to computations of the relaxations of all possible groups. So we turn to over and under approximated volumes and use these approximated ones to guide us select the groups for multineural relaxations method. It's the workflow of our dynamic selection figma. The figma firstly will compute the over and under approximated volumes of the relaxations from all possible groups of K. Then, based on these approximated volumes, our group selection strategy will select the groups with very small over-approximated volumes and eliminate the groups with very big under-approximated volumes. Then the selected groups are sent to the SPLM for the generation of corresponding multineural relaxations, which is 2K dimensional. And we can notice that we use the K-dimensional computation to substitute for the 2K dimensional computation. The over and under approximation are based on the approximation functions from vectors, especially for the under approximation one. And we improve the over approximation from vectors by utilizing the K-dimensional relaxations P, capital P, which is used in the SPLM. We mentioned before that the SPLM will first generate a K-dimensional relaxations among the activation inputs of K neurals, so that is capital P. And the volume of capital P can be exactly computed by off-the-shelf volume tools like Q-hole, because P is also a convex hole. We can see that our over approximation is tighter than the one from vectors because we consider the relaxations of activation inputs from K neurals, especially in the scenario of multineural relaxations computation. And we use these over and under approximated volumes, which has K-dimensional computation to reduce the 2K dimensional computations from those redundant or unnecessary relaxations. And you can find more detailed and proofs in the section 3.2 in our Figma paper. These are the experiments of our Figma paper, and we focus on the MNIST and the CIFAR10 data sets. They are data sets for the networks with the classified task. And the parameter k equals to 3, which is suggested in the Primar's paper, and it performs best in the experiments of the Prima. There are 3 verifiers concluded in our experiments. They are Prima OR, Prima Parallel, and Figma. Prima OR will compute all the relaxations from all possible groups of K. And it will make a lot of out-of-memory cases. Then the Prima Parallel is the static selection strategy used in Prima. And we use the same parameters in Prima Parallel, which are the same as the ones in Prima. Finally, the Figma is our dynamic selection strategy. We can see that according to the table, except for the out-of-memory cases, the runtime on average of Figma is less than the ones from other two, with negligible precision showed by the verified cases in the third line. And the groups generated from Figma are also less than the ones from other two. That's because our dynamic selection strategy will reduce some redundant relaxations and their groups according to the approximated volumes. We can see that the reason of the improvements of the Figma mainly comes from the reduced groups. And we noticed that, especially on the minist CIFAR big networks, the runtime on average of Figma is more than the one of Prima Parallel. That's because there are some out-of-memory cases happened in Prima Parallel due to the huge computations. Maybe the Prima Parallel used the static strategy will not select enough groups, and too many groups means too many relaxations should be dealt with, and it will cause the out-of-memory issues. The out-of-memory issues are not recorded in our experiments, and such cases need a lot of runtime. So that's the reason why the runtime of Figma is more than the Prima Parallel in this experiment, because the out-of-memory cases are not recorded in Prima Parallel. To further analyze the improvement of our Figma, we divide the runtime, into 3 parts. They are TGR, TCG, and TLP. The TGR is a time for neural grouping, and the TCG is a time for multineural relaxations generation. The TLP is a time for LP solving. LP solving is used by the linear program solvers. We can see that the TGR of Figma is more than the ones from the other two. That's because during the time for neural grouping, our Figma showed over and under approximated the volumes of relaxations for all possible groups. And the Figma should also select the groups according to least approximated ones. But it brings a lot improvements on both of the time for multineural relaxations generation and the time for LP solving. That's because our Figma will reduce the groups based on the volumes, and as a result, during the time for multineural relaxations generation, the groups should be dealt with by SPLM are reduced. And also, the relaxations should be dealt with by the LP solver are also reduced. So that's the reason why the increased TGR can bring the huge improvements for the TCG and the TLP, and the total runtime of Figma will be less than the times from the other two. In conclusion, we propose a kind of dynamic selection strategy named Figma for the multineural relaxations methods, and its key idea is to over and under approximate the volumes of relaxations from all possible groups of K-neurals. And our selection strategy will select the groups with very small over-approximated volumes and then eliminate the groups with very big under-approximated volumes. So the groups are reduced and the runtime is less than the static strategy with negligible precision. The experiments shows that our Figma is effective on runtime and have the competitive precisions. Thanks for your listening, and it's time for question and answering.
Thank you. Let's thank the speaker. Other questions? Any question on the relaxation? Relaxed question? No? I have a relaxed question. Where your system fails, your approximation fail, I mean, where you lose precision in such a way that you cannot prove what you want to prove. I mean, there is an approximation in your method, right?
Sorry, can you repeat?
Yeah, there is an approximation in your method. You have over and under approximate. Where it fails, I mean, what are the conditions, the input or the system where this may fail? How can I hack your system?
How can you hack?
Hack.
Yeah.
How can I
attack?
Break your system?
Yeah, I know attack means.
Yeah.
Yeah, I know. Thank you. How can I attack my system? Maybe. Oh, yeah, I have an idea. This is according to our detailed selection strategy. Yeah, like this. Maybe the attacker can, let us describe the selection strategy more detailed firstly. Our selection strategy is compared with, return a set of groups named G, capital G. And when there is a group candidate comes to G, and the candidate want to be selected, then we should compare the candidates over and under approximation volumes with the maxima under approximated volumes and the minima over approximated volumes among all the groups from G. So the interval of the groups of the volumes from the groups is the key for the actor to hack our system.
Wow.
If you because we will select the groups with very small over approximated volumes and eliminate the one with very big or under approximated volumes. If the hacker make the interval of the volumes too approached with each other, maybe our system can be more easily to be hacked.
Okay, thank you very much. Wonderful answer. Other questions? No? Okay, thanks, speaker.
Yeah, thank you.
I think SAS is over for today, and we'll see you tomorrow.